Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. Before time, before space, there was nothing. Not darkness, not a void in which something could drift, for even darkness and emptiness require a place to exist. It was a nothingness beyond comprehension, a silence so absolute that no thought or word could pierce it. In that great silence before creation, no light shone, no sound echoed. All the energies and forces we now know were dormant or absent, in a state that defies human language. It is the canvas of non-existence upon which our cosmos would one day be painted. What does it mean to be born from nothing? This question has haunted philosophers and scientists alike. In ancient myths, the world emerges from chaos, from a giant cosmic egg or the spoken word of a deity in the void. These are human attempts to grapple with the ultimate mystery, how something, the universe, reality, everything we know, could spring into being when there was no before, no bedrock of space or time. In the beginning of our scientific story, there is a similar mystery. The equations of physics whisper that time and space themselves began in a stupendous moment, leaving no trace of a prior era for us to read. If there was a before, it lies hidden behind a veil we cannot yet lift. One idea is that time itself began with the birth of the universe. Asking what came before might be as meaningless as asking what lies north of the North Pole. Another idea suggests our universe is one cycle in an eternal series, that the silence before the Big Bang was the echo of an earlier cosmos that ended, and from its demise, our own was born. In this view, nothingness might be more like a cosmic pause between breaths, the universe exhaling and inhaling over infinite eons. But these are speculations at the edge of knowledge. What we know is that roughly 13.8 billion years ago, the silence ended. Out of the void, a flash of creation erupted. In an immeasurable fraction of a second, the universe began. It burst forth from perhaps an infinitesimal point, smaller than an atom, with unfathomable energy. All the matter, energy, space, and time that now exists was concentrated in that embryonic cosmos. The nothingness, whatever it truly was, gave way to a fierce and blazing emergence. The universe was born from nothing, in the sense that no pre-existing space cradled it. It made its own space, it made its own time. That first moment was not a normal explosion in space, it was an explosion of space itself. Silence was replaced by a roar of creation, though there were not yet ears or air to carry sound. Darkness was replaced by a searing burst of light, though in truth, the infant universe was so hot that light was immediately trapped, tangled with matter. Still, we speak in metaphors because our minds need them. We imagine a great cosmic dawn breaking over an infinite expanse of nothing, heralding the start of everything. In reality, that dawn was everywhere at once, and the expanse itself was just coming into existence. From absolute silence and emptiness came a thunderous birth. In the first instance, the universe was a tempest of unimaginable energy. Time and space had just unfurled, and everything that would ever be was compressed into an inconceivably dense state. The temperature was so high that the known laws of physics melded together. Forces that today are distinct, gravity, electromagnetism, the forces that bind atomic nuclei, were unified in that newborn moment. There were no atoms, no particles as we know them, only a furious blur of pure energy. Then, in a brief flash of less than a trillionth of a second, something extraordinary happened. The universe underwent a growth spurt unlike anything since. We call this moment cosmic inflation. It may have been triggered when one of the fundamental forces, the strong nuclear force, snapped free from an earlier unified state, releasing an enormous energy that drove space to expand exponentially. Space itself expanded at a staggering rate, far faster than the speed of light. This did not violate any cosmic speed limit. Rather, it was space carrying matter along, stretching the very fabric of reality. In that infinitesimal blink, the universe grew from smaller than a subatomic particle to perhaps the size of a grapefruit or larger. To an outside observer, if one could exist, it would have looked like nothing one moment and an entire nascent universe the next. But there was no outside yet, for space itself was young and expanding. Why did inflation occur? What drove this wild expansion? These questions remain on the cutting edge of cosmology. Perhaps an exotic form of energy in the vacuum triggered it. A high-energy state of empty space that suddenly released its energy into the expansion of space. As inflation raged, it ironed out any irregularities. Just as a balloon, when blown up, smooths out its wrinkles, the inflating cosmos became extremely uniform. Any curvature or clumps were stretched thin. Distant regions that could never have contacted each other under normal expansion were, just moments before, intimately close together. Inflation flung them far apart, bestowing the universe with vast size and an almost featureless consistency. Almost, but not entirely featureless. Even in the raging furnace of the very early universe, randomness played its part. The quantum world, with its jittery, unpredictable fluctuations, left faint imprints on the density of that primordial energy. Tiny flickers, slight differences in density and temperature originating from the quantum foam of existence, were trapped and amplified by inflation. As space ballooned, those minuscule fluctuations were stretched to astronomical scales. Where there was ever so slightly more energy in the microscopic chaos, now there was a denser patch of universe. Where there was slightly less, a thinner patch. These differences were unimaginably small, mere 1 part in 100,000 deviations from perfect uniformity. Yet they were profoundly important. In time, those tiny wrinkles in the otherwise smooth cosmos would grow into galaxies, clusters, and great cosmic structures. In essence, cosmic inflation took quantum whispers and made them the blueprint for the stars and galaxies we see today. The inflationary burst was over almost as soon as it began, a fleeting cosmic heartbeat of expansion. When it ended, the energy driving it did not simply vanish. Instead, like a wound-up spring suddenly released, that energy transformed into an immense bloom of particles and radiation. The universe reheated. In that moment, what we typically think of as the Big Bang, a hot, dense explosion of matter and light, occurred. Space became filled with a high-energy plasma, a hot soup of particles. In that newborn fireball, matter and energy were interconvertible. Particles were created and destroyed incessantly. Quarks, electrons, antiquarks, positrons, photons, neutrinos, all kinds of exotic, fleeting particles roiled in a searing broth. Protons and neutrons did not yet exist as bound states. Instead, their constituents, quarks and gluons, swarmed freely. The temperature was on the order of billions upon billions of degrees. Matter and antimatter were being forged in almost equal measure, only to annihilate back into light. For every billion matter-antimatter pairs that annihilated, a tiny bit of matter, perhaps one particle, survived without a partner. That vanishingly small excess of matter was enough to ensure that our universe would not end up empty. It would become the stuff of stars and life. The universe almost became nothing again through mutual destruction, but thanks to that slight imbalance favoring matter, something remained. A few grains of matter per immense volume of energy, the seeds from which all galaxies, stars, and planets would later form. As fractions of a second turned into whole seconds, the universe continued to expand, though at a gentler pace than inflation's mad rush. With expansion came cooling. By the time the universe was 1 second old, it had cooled to billions of degrees and was still filled with a dense plasma of particles and radiation. In that first second, the basic forces of nature settled into their separate identities. Gravity had split off earliest, during inflation. Now the strong nuclear force and electro-weak force had also separated into the forces we know today: strong, weak, electromagnetic. The the stage was set for the next steps in cosmic evolution. Amid this churning plasma, something else important happened in those first seconds. Neutrinos, ghostly, nearly non-interacting particles, decoupled. These wisps slipped out of the dense throng and began streaming freely through space, barely impeded by matter. The universe became transparent to neutrinos almost immediately, at around 1 second old. Those neutrinos still travel today as an all-pervasive cosmic neutrino background, a silent kin to the light that would later be set free. They are hard to detect, but they remain one of the surviving whispers of the infant universe. The embryo universe, still less than a minute old, was immensely hot and bright. Quarks had begun to combine into triplets, forming the first protons and neutrons within the first millionth of a second, once the universe cooled below roughly 1 trillion degrees. Now, as time passed the mark of a few seconds, the frenetic particle-antiparticle annihilation ended. Most antimatter had paired off and disappeared in a flash of gamma rays, leaving that tiny surplus of matter. A sea of photons, light particles, dominated the energy content, but there were also countless neutrinos, and a growing number of protons, neutrons, and electrons. The raw ingredients of atoms, though not yet assembled into atoms. As the newborn universe moved from its first seconds into its first minutes, it continued to cool and expand. The frenetic collisions of particles began to slow just enough for new kinds of order to emerge. Around 3 to 4 minutes after the bang, the temperature fell to about 1 billion degrees, roughly 70 times hotter than the core of the Sun. Now atomic nuclei could begin to form. Protons and neutrons, freshly forged from quarks, found the universe cool enough to stick together under the embrace of the strong nuclear force. A second great creation event unfolded in this period. Big Bang nucleosynthesis, the formation of the first atomic nuclei. In the blazing furnace of these early minutes, protons slammed into neutrons and fused. Helium, the second simplest element, began to form in abundance. For a brief window of time, conditions were just right for nuclear fusion on a cosmic scale. Much as the cores of stars billions of years later would fuse hydrogen into helium, the entire young universe functioned like a star, converting the simplest elements into slightly heavier ones. Over about 17 minutes, most of the neutrons in the universe, which are unstable on their own and would decay if left isolated, managed to fuse into helium nuclei, each consisting of 2 protons and 2 neutrons, or a few other light nuclei. By the time this period ended, about 25% of the mass of ordinary matter had become helium nuclei, with the remaining 75% remaining as hydrogen nuclei, single protons. A trace of deuterium, heavy hydrogen, and lithium, with 3 protons, also formed. The universe's initial chemical makeup was set: predominantly hydrogen, a healthy dose of helium, and tiny traces of lithium and beryllium. After about 20 minutes, it had expanded and cooled too much for further fusion. The furnace of the Big Bang's beginning flickered out. At this point, the universe was still an extremely hot plasma. Imagine an extremely dense, opaque fog of charged particles, electrons, nuclei, and photons. It was as bright as the interior of a star, but no light could travel very far. Space was like a brilliant, blinding mist. Any photon, particle of light, that tried to go more than a tiny distance would smack into a free electron and scatter. The universe was opaque, a glowing fog of light and matter tightly coupled. To an imaginary observer floating at, say, 100,000 years after the bang, the surroundings would look like a uniform glow, as if you were embedded in the surface of a star. You wouldn't be able to see through it. The concept of distance beyond a certain point had no visual meaning because light hadn't yet broken free. The cosmos was radiating, but curtained by its own dense matter. However, the expansion continued, and with it came cooling and thinning of that particle soup. Thousands of years passed, then tens of thousands. During this epoch, the energy of the universe was dominated by radiation, light, which kept matter particles flying apart and resisted gravity's efforts to clump things together. But gravity was patiently tugging on the matter nonetheless, and as the universe grew, the density of radiation fell faster than the density of matter. About 50,000 years in, matter took over as the dominant component controlling the dynamics of the universe's expansion. The radiation era gave way to the matter era. This meant that at large scales, gravity now had the upper hand to start drawing matter together into the seeds of galaxies and clusters, though it would still be some time before these structures became pronounced, since everything was still mixed in the hot plasma. Fast forward to approximately 380,000 years after the Big Bang. The temperature had fallen to around 3000 K, about the surface temperature of a cool star, roughly an orange glow. At this point, something profound occurred. Electrons began to combine with nuclei to form neutral atoms. A proton capturing an electron makes a hydrogen atom. Helium nuclei capturing electrons make helium atoms. This process is called recombination, though it's really combination for the first time. With most electrons suddenly bound into atoms, they were no longer free to scatter photons at every turn. The cosmic fog lifted. The universe became transparent. It was as dramatic as night turning into day on a cosmic scale, except here it was a bright, hot fog turning into clear darkness. For the first time, light could travel great distances without being immediately absorbed or deflected. When the cosmic fog cleared, the light that had been trapped was released to fly freely through space. The universe was about 380,000 years old, and this was its first free streaming light, often called the first light of the cosmos. The entire sky everywhere would have glowed with a bright, warm radiance. If human eyes had existed then and could survive the conditions, they would have seen a soft, orange-white glow coming from all directions, like being in the middle of a vast glowing cloud. That glow was the combined light of the hot plasma, suddenly unleashed. As the universe expanded over time, this flash of light lost energy and shifted to longer wavelengths. What started as an intense orange-white glow stretched into a dimmer red, then into the infrared, and eventually, over billions of years, into the microwave part of the spectrum. Today, we detect this primordial light as the cosmic microwave background, CMB, a faint afterglow permeating the entire universe. The CMB is the oldest light we can see, a messenger from the cosmic infant years. It is extraordinarily uniform, with a temperature of about 2.725 K, just 2.7 degrees above absolute zero in every direction. Yet, it's not perfectly uniform. There are tiny variations in its temperature, only tens of microkelvins different, 1 part in 100,000 of difference. These subtle freckles in the CMB are the direct imprints of the quantum fluctuations from the time of inflation, imprinted on the matter distribution when the universe was young. Regions that are a hair hotter in the CMB correspond to slightly denser areas back then. Slightly cooler spots correspond to slightly less dense areas. These differences are only a fraction of a percent, but they are crucial. Over time, gravity will amplify those slight over and under densities into the cosmic structures we see today. When we map the CMB, as satellites like COBE, WMAP, and Planck have done, we are effectively seeing the seeds of galaxies and clusters, the universe's baby picture, with a mottling of warm and cool spots encoding the initial blueprint of cosmic structure. So at 380,000 years old, the universe has become a relatively cool 3000 K neutral hydrogen and helium gas, filling space almost uniformly, and it's transparent. The brilliant youthful glow has now faded into a dull red warmth, and then beyond visible light entirely. What followed is a period often poetically called the Cosmic Dark Ages. Why dark? Because now, with the primordial glow gone, there were as yet no stars or galaxies shining. The universe was transparent and dark. The gas was cooling. The light from the Big Bang was drifting outward, and redshifting into invisibility, and space was largely unilluminated, save perhaps for very faint glows from atomic transitions or cooling gas. Nothing like the bright lights of stars. An observer floating at, say, 100 million years after the Big Bang would see a black sky. The temperature of the background radiation would be a few tens of Kelvin, so mostly microwave radio waves, nothing to see with eyes. Yet all around, gravity was quietly working on the slightly denser patches of gas, drawing them inwards. Gas was not perfectly uniform throughout the universe. Those cooler, slightly denser regions of the primordial gas, the ones corresponding to slightly cooler spots in the CMB, exerted a bit more gravitational pull. They began to gather more gas from their surroundings. Invisible clumps of dark matter, more on this mysterious component soon, were also drawing gas into their deep potential wells. During these dark ages, the universe was like a calm night where nothing visible happens, but seeds are germinating under the soil. Gravity amplified the tiny variations, slowly but surely, pulling hydrogen and helium into ever-growing clouds and filaments. The distribution of matter started to resemble a spiderweb, dense nodes connected by filaments, with voids in between, though at this early time it was all still diffuse and no stars had lit up. After perhaps a few tens of millions of years, the largest of these gas clouds, particularly where the invisible dark matter had clustered strongly, grew dense enough at their cores to trigger a new phenomenon. The gas at the center of such a cloud, pulled in by gravity, began to heat up as it fell inward. Kinetic energy of infall converted to thermal energy. Eventually, one critical cloud crossed a threshold. Its core reached temperatures of millions of degrees and high pressure. Nuclear fusion ignited. A huge burst of energy was released from the core, and a delicate balance was struck between gravity and pressure. A star was born, the first star in the universe. In pockets across the cosmos, this process repeated. Wherever a pocket of gas became dense and hot enough, a new star lit up. The first stars were likely very massive, dozens or hundreds of times the mass of our Sun, because without heavier elements, like carbon or oxygen in the gas, it couldn't cool as efficiently, and thus fragments of collapsing gas clouds tended to be large. These first stars burned a bright blue-white, extraordinarily luminous, and very short-lived by stellar standards. One by one, like brilliant blue-white beacons, they pierced the cosmic dark. It was as if the universe saw the light of its first campfires, kindling in a vast, cold wilderness, points of illumination sparking up in the blackness. The era of rionization had begun. Each first star flooded its neighborhood with energetic ultraviolet photons. These photons had the power to ionize neutral hydrogen, that is, to knock electrons off atoms. The neutral gas around each new star became electrically charged, ionized once again, forming bubbles of plasma amidst the neutral background. Initially, these ionized bubbles were small, centered on individual stars or star clusters. But massive stars live briefly. In a few million years, many of them would have died in violent supernova explosions, enriching the surrounding gas with heavier elements like carbon, oxygen, and iron. New stars were born in those same regions, some a bit smaller and longer lived, thanks to the cooling effect of the newly introduced heavy elements. Over several hundred million years, more and more stars formed, and the ionized bubbles around clusters of stars grew and merged. As the first generation of stars grouped into the first proto-galaxies, their combined ultraviolet glow carved out ever-expanding cavities of ionized gas. Imagine the once neutral universe now being Swiss cheesed by growing holes of ionization. Finally, by around 1 billion years after the Big Bang, nearly all the remaining hydrogen in intergalactic space was ionized again. The universe became transparent to ultraviolet light as well, as the last fog of neutral hydrogen was banished from intergalactic space. The Dark Ages had fully ended. The universe was filled with starlight. During this epoch, the cosmic landscape transformed rapidly. Gravity pulled the early star clusters into tighter groups. These groups merged to form nascent galaxies. The first galaxies were smaller and more irregular than the grand spirals and ellipticals we see today. They often were chaotic assemblages of stars, blazing with the light of massive new stars and the explosions of supernovae. Over time, small proto-galaxies merged to form larger ones. The cosmic web, the large-scale structure of matter, became more pronounced. Filaments of dark matter and gas channeled material into the growing galaxies, while vast voids were emptied of matter as it flowed towards the filaments. Some of the early massive stars likely collapsed into black holes after they died. These could have become seeds for the supermassive black holes we find in galaxy centers today. Indeed, by as early as 700 million years after the Big Bang, we have evidence from quasars observed by telescopes that some black holes of billion solar mass scale had already formed and were devouring matter, shining as intensely luminous quasars. That indicates the assembly of galaxies and black holes was well underway very early. In those first billion years, the universe went from a dark, uniform fog to a web of glowing galaxies. It was a dramatic transformation, a kind of cosmic adolescence full of growth spurts and turbulence. Over the next several billion years, this web of structure became ever more complex and beautiful. Gravity and time together sculpted an immense cosmic architecture. Galaxies gathered into groups and clusters, and those clusters themselves drew together into larger complexes called superclusters. On the grandest scales, matter arranged itself in filaments and sheets, weaving around enormous voids. This pattern is the cosmic web. The web forms as the gravitational attraction of matter draws things together along the path of slight initial overdensities. Galaxies are not scattered randomly. They lie along these filaments. Where filaments intersect, we get clusters and superclusters of galaxies, immense nodes of the web. In between lie voids, vast regions with far fewer galaxies, as if the web's threads outline bubbles of nearly empty space. To visualize the cosmic web, imagine looking at a frothy foam or a network of neurons in a brain. Clusters and superclusters are like the knots, filaments like the threads between, and voids like the empty gaps. One filament can stretch hundreds of millions of light years from end to end. Observations have revealed structures such as the Sloan Great Wall and others that span over 1 billion light years. Chains of galaxy clusters lining up. The largest structures known, great walls of galaxies, huge quasar groupings, approach scales where the word structure itself starts to blur, because on scales above a few billion light years, the universe looks homogeneous. Still, these enormous formations amaze us. For instance, one huge grouping of galaxies called the Bootes supervoid, though it's a void, is so large and empty that if galaxies were peas scattered across space, it would be like an expanse, tens of millions of kilometers with only a handful of peas. It's a tremendous volume of space, with hardly any galaxies at all, akin to a great cosmic cavern. Within the filaments, galaxies continue to interact. Galaxy clusters, collections of hundreds or thousands of galaxies bound by gravity, form at filament intersections. Our own galaxy, the Milky Way, is part of a small cluster, or group, called the local group, which in turn sits on the outskirts of the Virgo supercluster, which itself is part of an even larger structure, often called Laniakea, a supercluster complex spanning 500 million light-years. Our local group contains the Milky Way, Andromeda, and dozens of smaller galaxies. Laniakea, a Hawaiian word meaning immeasurable heaven, includes the Virgo cluster and hundreds of other groups, all flowing within a common gravitational basin. It is just one of many superclusters in the observable universe. Even within our local group, cosmic evolution continues. The Milky Way and the Andromeda galaxy are drifting inexorably toward each other. In about 4 billion years, they will merge, forming a new, larger, galaxy. This will be a slow-motion collision. Stars are so far apart that few, if any, stars will hit head-on. But the two galactic disks will distort and blend, likely forming a big, elliptical galaxy with a new structure. Such mergers have happened countless times in cosmic history, especially in clusters where galaxies are crowded. It's one way galaxies grow and transform. Our own eventual merger is just a small chapter in the long story of structure formation, but it highlights that even galaxies themselves are impermanent, ever-changing. The cosmic web forms a sort of scaffolding that cradles everything that exists within the universe. And remarkably, the shiny galaxies we see, the gas, dust, and stars, are only a small fraction of the matter involved in this structure. There is an invisible component called dark matter that outweighs the ordinary matter by about 5-to-1. Dark matter neither emits nor absorbs light, so we don't see it directly, but its gravity betrays its presence. It was dark matter that seeded the cosmic web. During the Dark Ages, dark matter clumped under gravity. It does not interact via light or pressure, so it started collapsing even when normal matter was still a hot plasma. These dark matter clumps served as gravitational wells, pulling in ordinary gas after it became neutral. Without dark matter, the gas alone might have taken much longer to form stars and galaxies, but with it, structure formation was boosted. Every galaxy sits in a cushion of dark matter, a dark halo, much more massive and extended than the galaxy's visible extent. In clusters of galaxies, the combined dark matter of the cluster creates deep potential wells that hold the cluster together. In fact, observations of galaxy clusters in the 20th century first provided evidence of dark matter. Galaxies were moving too fast to be held by visible matter alone. So one can picture the cosmic web as an invisible framework of dark matter, upon which gas settled and cooled to produce galaxies. The luminous matter traces the patterns drawn by dark matter's gravity. By around 5 billion years after the Big Bang, many of the structures we see today were in place. The cosmic web was well established. Galaxies had matured and grouped into clusters and superclusters. Stars had been forming for billions of years in those galaxies. In fact, the peak of star formation in the universe likely occurred around 3 to 4 billion years after the Big Bang, when galaxies were in a star-bursting frenzy. After that peak, star formation gradually declined as the gas reservoirs in galaxies were used up or heated or expelled by various processes. In fact, around this midpoint in cosmic history, the conditions were ripe for planetary systems like our own to form. Generations of earlier stars had enriched the interstellar gas with heavy elements, carbon, iron, oxygen, etc., forged in stars and supernovae. In one typical spiral galaxy, our Milky Way, a cloud of such enriched gas and dust collapsed around 4.6 billion years ago to form a new star, our Sun, and a retinue of planets. This was possible because at least 9 billion years had passed since the Big Bang, allowing multiple cycles of star birth and death to scatter the ingredients for planets. Our Sun lit up in a relatively quiet corner of the Milky Way, and around it formed a system of planets, including Earth. On that young Earth, formed from cosmic dust and the debris of earlier stars, complex chemistry began to brew in its oceans and atmosphere. By a few 100 million years after Earth's formation, life arose, simple at first. Over eons, that life became more complex, leading to creatures that could look up and marvel at the stars. In this way, we humans are very much a product of cosmic evolution. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in long-dead stars and scattered through space, incorporated into the Sun and Earth, and ultimately into us. Our emergence is an exquisite example of the universe giving rise to organized complexity capable of contemplating itself. While this was happening on the scale of galaxies and life, another, even larger scale drama was unfolding in the background: the expansion of the universe itself. Since the Big Bang, the universe has been expanding, but for a long time, It was expected that this expansion should be slowing down due to the pull of gravity. Indeed, for the first few billion years after the Big Bang, the expansion was decelerating. The mutual gravity of all the matter in the cosmos was putting the brakes on the expansion. Galaxies, though being carried apart, were doing so at an ever-slowing rate. One might have imagined that given enough time, the expansion might even stop and reverse if gravity was strong enough. However, about 6 or 7 billion years after the Big Bang, roughly at the time our Sun formed, something curious started to happen. The expansion began to speed up again. Galaxies started to recede from each other faster and faster. This discovery, made by observing distant exploding stars, supernovae, in the late 20th century, was revolutionary. It implied the presence of a new ingredient in the cosmic recipe, something pushing the universe outward. We call this mysterious influence dark energy. Dark energy is the name we give to the unknown cause of the accelerated expansion. It appears to act much like what Einstein once hypothesized as a cosmological constant, an intrinsic energy of empty space. Einstein originally introduced such a term to allow for a static universe, then removed it when expansion was discovered, reportedly calling it his biggest blunder, not realizing the universe actually does have a similar effect present. Dark energy doesn't dilute as the universe expands. It remains, as far as we can tell, constant in density. As space grows, the total amount of this energy increases, because more volume times the constant density yields more energy. In effect, dark energy is like an anti-gravity pressure uniformly filling space, pushing things apart. For the first several billion years, dark energy was negligible compared to matter. Matter's gravity was slowing the expansion. But as matter spread out and its density dropped, dark energy eventually became significant. About 5 billion years ago, dark energy's repulsive effect overtook the self-gravity of matter in the universe. The expansion, which had been slowing, stopped decelerating and began to accelerate. Small distances, like within galaxies or clusters, weren't affected. Those structures are bound by much stronger local gravity. But on large scales, between clusters and superclusters, the gaps began to widen faster and faster. To picture the effect of dark energy, imagine the universe's expansion as a ball that was thrown upward, the Big Bang being the throw. First, the ball climbs, but slows, gravity's pull. Then, unexpectedly, it starts accelerating upward as if pulled by an unseen force. Dark energy is akin to that unseen force accelerating the expansion of the cosmic ball. Another analogy. Think of 2 points in space with a spring between them, gravity, and an expanding rubber sheet under them, space itself expanding. Initially, the spring slows their separation, but if the rubber sheet's stretching, dark energy, grows strong enough, it will overcome the spring and the points will fly apart faster and faster. The simplest form of dark energy, consistent with observations, is a true cosmological constant, an unchanging energy woven into the fabric of space-time. If that is the case, then the fate of the universe is a continual acceleration. Distant galaxies will recede at ever-increasing speeds. Eventually, far in the future, distant galaxies currently visible will be carried beyond our horizon of visibility because space is expanding so fast that light from them can no longer reach us. The night sky over tens of billions of years will grow emptier as galaxies vanish from view one by one. Today, dark energy makes up about 68% of the total energy content of the universe. Matter is about 32%, of which about 27% is dark matter and 5% normal matter. Thus, the cosmos, by composition, is mostly this invisible, dark energy. It's astonishing. All the galaxies, stars, gas, and dust, everything we see, is only a trace component. Yet, it is thanks to that small component that we have structure and life. Dark energy, ironically, mostly influences the voids and the eventual destiny. Even now, dark energy's presence is subtle on human timescales. The Milky Way and Andromeda will still collide despite cosmic expansion because they are gravitationally bound strongly enough to overcome expansion at local scales. The local group of galaxies will remain together, but clusters that are not bound to us will drift away. For instance, galaxies in the Virgo cluster, tens of millions of light-years away, will recede further. In a few 100 billion years, should any observers be around, virtually all galaxies beyond the local group will have disappeared from view, being carried away faster than light can catch up. To summarize the cosmic inventory and its effect, dark matter provided the scaffold for structure and still holds galaxies and clusters together. Dark energy drives the overall expansion ever faster. Normal matter, atoms, forms the stars, planets, and living beings. Each plays a role in the grand cosmic story. Dark matter pulled the cosmos into a beautiful web. Normal matter lit that web with stars. Dark energy is now pulling the web apart at its largest scales. Time marches forward, and with it comes change. But why does time have a direction at all? We recall the early universe was an extremely hot, uniform state. And now we have a clumpy cosmos and cool expanses. Things have clearly moved from a state of order to increasing disorder. This one-way progress is encapsulated in the concept of entropy. The second law of thermodynamics says entropy, disorder, tends to increase in a closed system. This law underpins the arrow of time. Eggs break, but do not unbreak. Cream disperses in coffee, but never spontaneously gathers back at the top. A piece of paper burns to ash and smoke, but the ash and smoke won't reconstitute into paper on their own. These processes involve increasing entropy, and they define an irreversible direction to time, from past, lower entropy, to future, higher entropy. The universe as a whole began in a state of incredibly low entropy. At the moment after the Big Bang's initial inflationary smoothing, matter and radiation were almost perfectly uniformly spread. Paradoxically, uniform gas is a low entropy state in cosmology because gravity can do a lot of work with it. Imagine a smooth spread of matter that can clump versus matter already clumped into black holes. The latter is a higher entropy state gravitationally. The early universe had very low gravitational entropy, everything spread out smoothly, and not maximal thermodynamic entropy either. There were temperature differences and lots of free energy available. This special beginning, perhaps set by inflation or whatever preceded it, is why there was an arrow of time. The cosmos started wound up, like a clock with a lot of free energy and potential to evolve into more disordered states. As the universe aged, entropy increased. The formation of stars and galaxies might seem like an increase in order locally, but overall, entropy rose because, for example, when a star shines, it produces a lot of thermal radiation, high entropy, out of nuclear fuel, lower entropy state. The light that escapes into space carries away entropy. The net effect of all processes, gravitational clustering, star formation, life, has been to increase total entropy. Entropy is now vastly higher than in the pristine early universe, and it will continue to increase. What is the ultimate fate implied by ever-increasing entropy? It is often called the heat death or big freeze. This scenario is a universe where, on the largest scales, everything becomes uniform again. Not in a low entropy way like the beginning, but in a maximum entropy way. A thin mist of particles and radiation at near uniform temperature, with no gradients to power any process. If dark energy continues to accelerate expansion forever and nothing intervenes, this is the likely end state, trillions upon trillions of years hence. Let's trace that future vision. First, over the next few trillion years, star formation in galaxies will taper off. Galaxies have a finite supply of gas to make new stars. Eventually, that gas runs out or becomes locked in stellar remnants. The longest-lived stars, small red dwarf stars, can burn for trillions of years, far longer than the current age of the universe. So, billions of years from now, Galaxies will be dominated by long-lived red stars, slowly fusing hydrogen. As time marches on, even these will exhaust their fuel. By around 100 trillion years from now, 10-14 years, the era of star formation will officially end. We enter the so-called degenerate era, dominated by stellar remnants. In that far future, the galaxies, those that remain gravitationally bound, like our future Milkdromeda, the merged Milky Way Andromeda, will be populated only by degenerate objects, white dwarfs, cores of spent stars, neutron stars, brown dwarfs, failed stars, and black holes. New stars will no longer be born. The remaining stars will slowly cool and dim. White dwarfs, starting hot, will radiate their energy over billions and trillions of years, turning into black dwarfs, cold, dark, stellar embers. Planets, if any still orbit, will gradually spiral into their stars or be flung out by gravitational encounters over extremely long timescales. At this point, entropy is still increasing. Complex structures decay. Perhaps some hypothetical, incredibly long-lived civilization might find ways to survive around fading sources of energy, but eventually usable energy supplies would dwindle. After many trillions more years, even larger structures start to destabilize. Gravitational interactions within what's left of galaxies will gradually eject many objects into intergalactic space, a process called dynamical relaxation. Central black holes might collect some matter, while other stars or remnants are thrown to the outskirts or beyond. Fast forward to unimaginably distant times, 1019, 1020, up to 1040 years. By 1020 years, most galaxies as we know them may disperse, stars either fallen into central black holes or scattered. Around 1040 years, a number so large it defies comprehension, even protons, if unstable, some particle theories suggest protons might eventually decay, will have decayed into lighter subatomic particles. If proton decay is real, at this point, solid matter dissolves. Planets, white dwarfs, any remaining asteroids or dust, all would literally evaporate into radiation and elementary particles. The universe becomes a dilute soup of electrons, positrons, neutrinos, and photons, perhaps with some lingering protons if they're absolutely stable, and lots of dark matter particles. Assuming dark matter is stable and doesn't decay, we aren't sure, but likely it is stable. One might think black holes would still be around as massive reservoirs of mass, even after normal matter is gone. And they will, for a long time. But even black holes aren't eternal. Stephen Hawking theorized that black holes slowly evaporate by emitting Hawking radiation, a very slow quantum thermal glow that causes them to lose mass over time. For stellar mass black holes, the evaporation time is around 10^67 to 10 years. For supermassive black holes, millions or billions of solar masses, like in galaxy centers, the time is stupendously larger, on the order of 10^98 to 10^100 years or more. But given enough time, even these giants will eventually evaporate completely, each ending in an explosive burst of high-energy particles when its mass becomes very small. After the last black hole has vanished, the universe enters its final stretch, the dark era. The temperature everywhere will approach an extremely low value as expansion dilutes any remaining energy. Essentially, what remains is a sparse sea of photons, mostly of extremely long wavelength radio waves. Some electrons, positrons, neutrinos, and perhaps some dark matter particles if they haven't decayed, all spread so thin that in a volume the size of our Earth, you might find essentially none of those particles. Entropy is maximized. In a sense, the cosmos returns to a featureless state, not of super-hot plasma like the beginning, but of near-empty cold space. All gradients of temperature or density are ironed out. With no free energy differences, no work can be extracted to power any process. Change virtually halts. This is the heat death. Time would still pass, but nothing of significance would mark its passage. It's a ghost universe, silent, empty, and everlasting, unless some fluctuation eventually breaks the stalemate, which we'll touch on. The arrow of time at that point would effectively cease to matter, because there would be no events to distinguish past from future. The great cosmic drama would have quietly exited stage right. However, this fate assumes a constant dark energy and no new physics intervening. We must acknowledge other possibilities. The universe's end might be more dramatic or lead to a rebirth. One such possibility is the Big Rip scenario. If dark energy is not constant, but instead grows in strength, for example, its equation of state has W1, a so-called phantom energy, the acceleration would become more and more violent. Eventually, even gravitationally bound systems would not hold together. In a Big Rip, first clusters of galaxies would be torn apart, galaxies receding from each other despite being bound, effectively overcoming their mutual gravity. Next, galaxies themselves would be shredded, stars flung out as the space within the galaxy expands faster than the galaxy's gravity can keep up. Closer to the rip, solar systems would unbind, planets would fly off from stars. In the final moments, stars and planets would be ripped apart, and even atoms and atomic nuclei would be sundered in the ultimate blow. The timeline for such an event depends on how phantom the dark energy is. If it were just slightly more negative than 1 in its equation of state, the Big Rip might be trillions of years away, or not happen at all, if it tends asymptotically to a constant. If it's substantially more negative, the rip could happen sooner, though current data suggest dark energy is very close to a cosmological constant, One. The concept is spine-chilling, the fabric of space accelerating so wildly that it rips apart anything bound. Matter is literally disassembled by the expansion of space. Most physicists consider this unlikely based on current evidence, but it's not ruled out absolutely. If our current best fit is slightly off, the cosmos might end not in ice, but in a singular crescendo of tearing apart everything. Another scenario, the Big Crunch. This is in a sense the opposite of heat death or Big Rip. It's a reversal of the expansion into a contraction. If, for some reason, dark energy were to dissipate or turn attractive, and if the density of matter were high enough, gravity would eventually win out and pull everything back together. The expansion would slow, stop, and reverse. Distant galaxies would start to approach rather than recede. Over billions of years, what was once an expanding universe becomes a collapsing universe. Galaxies would rush together. Clusters merge into a supercluster, superclusters into huge sheets, and finally all material closes in. The temperature of the background radiation, which had been dropping for eons, now starts to rise again as space compresses that radiation. The dark, quiet cosmos would light up once more as every particle of light gains energy and blue shifts. Galaxies might careen into each other with increasing frequency. The night sky would glow brighter and brighter as more galaxies cram into our observable view, and the heating of all gas triggers star formation, or makes existing stars shine more fiercely. In the far future of a Big Crunch, the universe's scale continues to shrink. What were galaxy superclusters a few billion years before are now overlapping and colliding. Eventually, all matter might coalesce into an extremely dense state. The temperature would soar to star-like or greater levels everywhere, ionizing whatever atoms existed once more. Fusion could ignite in giant bursts as gas clouds compress. Essentially, the reverse of the universe's expansion timeline happens. Clusters of galaxies collapse into blazing quasars, then into massive nebulae, then into a shrinking ball of plasma, then perhaps into conditions similar to the very early universe. If quantum gravity or other effects don't intervene, this collapse could lead all the way back to a state of seemingly infinite density and temperature. Essentially, a mirror image of the Big Bang, sometimes dubbed the Big Crunch. Is that truly an end, or could it be a bounce? Some modern theories speculate that a Big Crunch could transition into another Big Bang, the death of one universe seeding the birth of a new one. In cyclic models, the universe might undergo endless, or at least many, bang crunch cycles. Ancient cosmologies, like Hindu cosmology, imagined time as cyclical, cosmic days and nights of Brahma, with universes expanding and contracting periodically. A scientific version might be, after a crunch, all space and time re-expand again, maybe after reaching a singularity, or perhaps never fully reaching infinite density because new physics causes a rebound. If there is a bounce, the astonishing implication is that our Big Bang might not have been the absolute beginning, but simply the latest bounce. Some theorists working in quantum cosmology and string theory have explored models where, for example, our 3D universe, brain, periodically collides with another brain, causing big bangs in a cycle. Others, loop quantum cosmology, find that quantum effects could cause space to repel at extremely high densities, avoiding a singularity and starting expansion anew. If the universe can bounce, what happens to entropy and the arrow of time in such a cycle? That's a tough question. Naively, entropy would carry over and increase with each cycle, which would be problematic. You can't cycle indefinitely if entropy irreversibly accumulates, unless the bounce somehow resets the entropy or disposes of it. Some proposals, like conformal cyclic cosmology, Roger Penrose's idea, suggest that at the end of a heat-death scenario, when the universe is nothing but photons and essentially devoid of scales, it might be possible to relabel that state as the initial singularity of a new Big Bang. Since a universe of only structureless photons has no concept of time or size, it could be equivalently reinterpreted as a new Big Bang state. This is speculative and not widely accepted yet, but it shows how creative thinking is being applied to the idea of cosmic rebirth. There are also other theoretical fates. One is a vacuum decay scenario. Perhaps our current vacuum, the ground state of fields in the universe, is not the true lowest energy state. If there exists an even lower state, the universe could at some point quantum tunnel into that lower state. If that happened, a bubble of true vacuum would appear somewhere and then expand at near the speed of light, converting everything it touches into a new state of being. Within that bubble, the laws of physics might be different constants, particle arrangements. So essentially, it's like a new universe erasing the old one. This bubble nucleation and expansion would be catastrophic, from our perspective, and extremely fast. One moment everything's fine, the next, a bubble of alien vacuum is rushing through you, disintegrating you, Earth, and every structure, and we'd never see it coming because it expands at light speed. It's a wild idea, but certain particle physics models make it a possibility. For instance, if the Higgs field sits in a metastable false vacuum. Current data suggests it's not highly likely in the near term. If it can happen, it might be trillions of years away or more. Or maybe it's truly stable and won't happen at all. In any case, it's another way nothing, or rather a different something, could be born from our something, effectively resetting the cosmic stage abruptly. Finally, even in the heat-death scenario, some have mused about the possibility of random fluctuations creating new ordered patches. Given infinite time in a static de Sitter universe, the end state with dark energy domination, quantum fluctuations could occasionally, by sheer chance, produce a small region of lower entropy, perhaps even a new Big Bang seed, or a so-called Boltzmann brain, a spontaneously formed self-aware entity out of chaos. While these ideas are thought experiments and lead to some absurd-sounding consequences that physicists debate, often to argue that an eternal de Sitter phase might be problematic or that some new physics must intervene before infinity, they speak to the richness of considerations about eternity. Even in an endless nothingness, given unlimited time, perhaps a fluctuation might trigger a new creation event. The probability is incredibly low for any given moment, but in infinite time, the unlikely becomes inevitable. So perhaps heat death isn't truly the end. It could be a plateau before another beginning, in an endlessly cyclic multiverse of fluctuations. This is deeply speculative, verging on philosophical, but it shows that even finality might not be absolute. At this juncture, We've painted possible endings, eternal expansion into heat death, a big rip, a big crunch with possible bounce, or a transition to something entirely different. Each path carries different implications for the arrow of time and for the question of whether the universe has a purpose or just a lifespan like any other natural phenomenon. From what we can tell now, with our cosmological measurements, the most likely fate is an ever-accelerating expansion leading to a very cold, very empty universe. Heat, death. But our knowledge is incomplete. Dark energy could surprise us by changing behavior. New physics, like interactions between dark energy and matter, or a slow dilution of dark energy, could alter the story. Now, let's step beyond even these questions of our universe's fate and ask, is our universe the only universe? For much of our narrative, we presumed that the universe meant all that exists. But modern physics has opened the door to the idea of a multiverse, a larger reality in which our universe is just one part. There are actually different notions of multiverse that scientists discuss. One arises from quantum theory, the many worlds. Interpretation suggests that all possible outcomes of quantum events actually occur, each in its own separate branch of reality. In that view, reality continually splits into a vast ensemble of parallel timelines. That's a kind of multiverse, a branching tree of universes coexisting in superspace. It's a very different concept from universes separated by space. It's more like parallel dimensions or alternate histories. It might not affect our cosmic story directly, so let's set that aside after noting it as an intriguing possibility. Parallel universes where, say, different events happened in history, etc., playing out side by side unbeknownst to each other. The multiverse idea, more relevant to cosmology, arises from cosmic inflation and string theory. If inflation occurred as our theories suggest, the ultra-fast expansion in the universe's infancy might not have been a one-time event that ended everywhere at once. There are strong reasons to suspect inflation is eternal. While it ended in our region, allowing our Big Bang fireball to proceed, in other far-flung regions, inflation might still be going on, endlessly creating more bubble universes. Picture a vast, inflating space-time, a kind of ever-growing foam. Occasionally, in that foam, regions stop inflating and crystallize into hot Big Bang bubbles like ours. Each bubble is a universe in its own right, with potentially different properties depending on slight quantum variations when inflation ended there. Our observable universe would be just one bubble that happened to nucleate 13.8 billion years ago. There could be countless others. These other universes are not located in our space. They are separated by continuing inflating space, which expands so fast that we can never catch up to the neighboring bubbles. They are forever out of reach. Each bubble might have different physical constants, particle content, even dimensionality, especially when combined with ideas from string theory. String theory suggests that the vacuum of the universe, the configuration of extra dimensions and fields, could have many possible states, sometimes quoted as 10 to 500 or more possibilities in the landscape of string theory solutions. Each bubble universe could realize one of those many possibilities. That offers a tempting explanation for why our universe has the peculiar laws it does. If there is a multiverse of all kinds of universes, we just happen to be in one that had the right conditions for galaxies, stars, and life, because otherwise we wouldn't be here to observe it. This is a kind of anthropic selection from a multiverse ensemble. It's important to note, none of this multiverse speculation is confirmed, but it is grounded in serious physics theories. Eternal inflation is a rigorous outcome of many inflation models. Once inflation starts, it generically doesn't stop everywhere, so while one bubble forms, inflation continues elsewhere, leading to potentially infinitely many bubble universes. And in string theory, the many possible shapes of extra dimensions, each giving rise to different physical constants, combined with inflation, virtually guarantees a multiverse. The inflating space fills itself with regions realizing all those options. Can we detect or observe evidence of other universes? It's challenging by definition. If they are truly separate, we can't see into them. But one possible sign would be if a neighboring bubble universe in the early inflationary period happened to collide with our bubble. That collision might leave an imprint, perhaps a circular pattern or a particular kind of distortion in the cosmic microwave background. People have actually searched CMB maps for hints of such collisions. So far, none have been convincingly found, but the search exemplifies how we don't shy away from trying to test even outrageous-sounding ideas. Another hint could come from the distribution of gravitational waves or subtle effects on the distribution of galaxies, none detected yet in a way that screams other universe. Another multiverse notion comes from higher dimensions and brane world scenarios. String theory requires extra spatial dimensions, 6 or 7 beyond our usual 3. Those dimensions could be compactified, curled up small, or in some models, we could be confined to a 3D brane floating in a higher dimensional space. There could be other branes, essentially other universes, separated from ours in the extra dimensions. Normally, we'd have no interaction with them except perhaps gravity, which can propagate in the higher dimensional bulk. Some have even imagined that a collision between branes could be what the Big Bang was. 2 3D worlds collided, releasing energy that flooded our brain with the hot matter of a Big Bang. If those other branes, universes, exist, they are right next door, in a sense, perhaps only a tiny distance away in a 4th spatial dimension. But we can't see them or touch them because our particles and light are confined to our own brain. It's a mind-bending concept. Other entire universes, potentially a millimeter away from us, in a direction we can't perceive. Whether it's bubble universes, parallel quantum worlds, or higher dimensional brane worlds, the multiverse idea profoundly changes the context of our cosmic story. Our universe could be a small chapter in an infinitely larger ensemble. It could mean that what we consider the ultimate beginning, the Big Bang, is just one local event in an eternally evolving multiverse. And it forces interesting questions. If there are countless universes, each with possibly different physics, what does that say about meaning? One could imagine each universe as having its own narrative, its own potential for life, or even intelligence. Are there other conscious beings out there, not just in our universe, perhaps in distant galaxies, but in entirely separate universes, forever causally disconnected from us? This drifts from science into philosophical wonder, because by construction, we may never verify those other universes. Yet, the theories that predict them, inflation, quantum mechanics, string theory, are in principle testable in other ways and have earned credibility. So we take the multiverse seriously, while acknowledging it currently lies at the speculative frontier. Regardless of whether there's a multiverse, we find ourselves in this universe, with its particular story. From a singular beginning, or at least an extremely hot, dense early state, our universe expanded, cooled, formed structures, and eventually produced us, beings capable of reflecting on the whole process. We've gone from contemplating mythic cosmologies to actually measuring the geometry and expansion history of the cosmos. We discovered the universe had a beginning, Big Bang, that it is 13.8 billion years old, that it expands, that it has a cosmic web of structure, and that it is dominated by dark matter and dark energy. These are incredible revelations, won through the hard work of observation and theory, building on generations of curious minds. Now we turn to the philosophical and existential implications of the cosmic story. Standing under the night sky, we can feel 2 seemingly opposite emotions: insignificance and profound connection. On one hand, the universe is vast beyond imagination. The Earth is a tiny pebble in a gigantic space. Even our galaxy, with 100 billion stars, is just one in a sea of billions of galaxies. Physically, We occupy no privileged position. The cosmos is not arrayed with humanity at the center. We are off in a corner of an average galaxy, which itself is in a supercluster that is unexceptional among others. Time-wise, human history is an eye blink compared to cosmic time. The stars shone for billions of years before we came along. They will continue billions of years after we are gone. It's humbling, even daunting, to recognize this. The famous pale blue dot photograph taken by Voyager 1 from beyond Pluto, showing Earth as a tiny bluish speck in the void, encapsulates that humility. All of human history, every joy and sorrow, every hero and villain, played out on that mote of dust, suspended in a sunbeam in the vast darkness. When confronted with such scale, it's natural to feel small. Yet, on the other hand, how marvelous that we can comprehend this scale. We are made of particles that were forged in stars. Essentially, the universe gave birth to conscious organisms that can observe and contemplate the universe. We are a way for the cosmos to know itself, a sentiment popularized by Carl Sagan and profoundly true. Our atoms originated in the Big Bang, hydrogen, or in stellar furnaces, carbon, oxygen, nitrogen, etc., or in supernovae, iron, zinc, iodine, gold, all the heavier elements. We are literally children of the stars, made of stardust. Through us, the materials of the universe have become aware and curious. That imbues us, and possibly other intelligent life out there, if it exists, with a kind of cosmic significance, albeit a self-bestowed one. We carry the legacy of 13.8 billion years of cosmic evolution in our bodies. When we gaze out at the galaxies, those galaxies are in a sense observing themselves through our eyes. The emptiness of space, while vast, is not completely empty. It's filled with fields and particles and possibilities. Likewise, the perceived emptiness or pointlessness one might feel when confronted with a giant, cold universe can be filled with our own meaning and purpose. The cosmos doesn't hand us a script. Instead, it gives us the stage, the raw materials, and the invitation to create meaning. And humans have been doing that for as long as we have existed, through story, science, art, love, and exploration. We find that the more we learn about the universe, the more beautiful it becomes. Consider the fact that the atoms in your body were once inside of a star, perhaps many different stars over the eons. In a very real sense, you are as old as the universe, because the matter that composes you has been around since the beginning, apart from some recent transmutations via nuclear reactions. We are deeply connected to the cosmos. Every breath you take contains atoms from all over Earth and beyond, even some noble gas atoms that were forged in the Big Bang. The water you drink contains hydrogen made at the dawn of time. The calcium in your bones was fused in some star that ended its life long before Earth formed. We are a microcosm of the universe. This perspective can evoke a sense of spiritual awe, even in a non-religious framework. It's the awe of existence itself, the recognition that we are part of something vast and magnificent. The American astronomer Harlow Shapley said, "We are akin to the totality of things. The atoms don't belong to us, we belong to them. We are a moment in their journey." The universe's story also imparts lessons. One is the transient nature of all things. Stars are born and die. Even galaxies collide and merge. The universe evolves. Change is the rule. On Earth, we see that civilizations rise and fall, species come and go, all part of that cosmic change. But amidst change, there is continuity. The continuity of matter and energy, and the continuity of information passed on. Our sun inherited matter from previous stars. We inherited molecules from Earth's past life. We pass our atoms back to the Earth when we die. It's a kind of immortality, not personal immortality, but the persistence of our substance and our influence. A star that died billions of years ago in our region of the galaxy, by dying, it seeded the cloud that formed our solar system. In a way, That star lives on through us. Likewise, the choices we make and the knowledge we gain might propagate far into the future, indirectly shaping things we will never see. When we build a telescope and discover something, that knowledge changes the consciousness of humanity, which may alter our future actions and fate. Our cosmic understanding has also, interestingly, circled back to some ancient wisdom. Many cultures intuited a connectedness of all things, or a cycle of creation. The scientific specifics we've learned differ from the myths. The universe isn't literally the egg of a giant bird, for instance, but the emotional thrust that we are part of a greater whole is affirmed more strongly than ever by science. We now see that the same physical laws apply everywhere. We've sent probes to other planets and found familiar chemical processes at work. We've detected light from atoms in distant galaxies and found the same spectral lines as atoms we study in labs. The universe has a unity, and the story of cosmic evolution is a single, continuous narrative from the Big Bang to the present and onward to possible futures. We are a chapter in that narrative. In contemplating the end scenarios like heat death or Big Rip, one can feel despair. Will it all amount to nothing? But one might also find liberation in it. The distant future is beyond our control. What matters is what we do with the time and universe we have. The fact that the universe will end in one way or another does not negate the preciousness of its present. In fact, it enhances it. Just as mortal beings find meaning in life partly because it is finite, the finite window of a lively universe can galvanize us to appreciate its wonders all the more. We live in a cosmic springtime, when conditions are just right for complexity and life. It will not always be so, but how fortunate that it is so now, and that we are here to witness it. There's also a school of thought that even if our universe fades, perhaps life, or an advanced form of intelligence, could in some way continue or influence beyond its own universe. Some speculative ideas suggest extremely advanced beings might even hop between universes or create baby universes artificially. These ideas blur science and philosophy and remain in the realm of imagination for now. But the mere consideration expands our sense of possibility. Perhaps the end of the universe isn't an absolute wall, but just another frontier to transcend for a sufficiently ingenious civilization. It sounds like science fiction, and it certainly is right now, but who can definitively say what a Type 3 or Type 4 civilization, if it could exist, might achieve after millions or billions of years of evolution? Bringing our thoughts back to the here and now, the night sky. It connects us to all of this grand history and future. When you next stand under the stars on a clear night, think about the journey of a photon that enters your eye. Perhaps it left a distant galaxy when that galaxy was young and our planet not yet formed, traveling across expanding space for tens of millions of years, through voids and past clusters, until finally, one night, it ended its journey on your retina, triggering a chemical reaction that led to an image in your brain. In that moment, you, a being of stardust, assembled on an 8-planet minor system around an unremarkable star, catch a whisper from the other side of the universe. And with collective effort, humanity has learned to interpret these whispers, to tell a coherent story of how we came to be. The cosmos is mysterious and beautiful. Every discovery seems to open new questions. We determined the age and shape of the universe, only to find most of its content is invisible, dark matter and dark energy. We may solve dark matter, perhaps a type of particle, and dark energy might remain puzzling or turn out to be a property of space itself. We look for potentially habitable exoplanets, wondering if life arose elsewhere. We tune our radios for possible signals from other civilizations, not knowing if we are alone or one of many. We delve into the quantum foam, attempting to reconcile general relativity, our theory of the very large, with quantum mechanics, the theory of the very small, hoping for a deeper understanding that might unify forces or reveal why the Big Bang happened the way it did. the quest goes on. Through it all, there is a human element that persists: wonder. As the astronomer Maria Mitchell said, "We reach forth and strain every nerve, but we seize only a bit of the curtain that hides the infinite from us." Yet, that bit of curtain has revealed an awful lot, and we continue to gently pull at it. Will we ever see the infinite, or the true beginning, or the full scope of the multiverse? Perhaps not, but the pursuit is part of what makes us human. The same impulse that made our ancestors paint constellations on cave walls and craft stories of creation now drives rockets and equations toward the heavens. Ultimately, the story of the cosmos is meaningful to us because it is also our story. We are not mere spectators. We emerged from this grand process. The hydrogen in our bodies, in every molecule of water, for instance, comes straight from the Big Bang. That means a part of us is as old as time. The carbon in our cells was forged in stellar hearts, making us the heirs of those stars. When we die, our atoms will return to the Earth, and eventually some will drift out to space again, maybe to become part of a new star or planet eons hence. In that sense, we are immortal, though our forms are temporary. So, what does it mean to be born from nothing? It means that existence is a gift against all odds, a tiny realm of something in an infinite sea of nothing. It means that perhaps nothing is unstable or pregnant with potential, that even a void can give rise to worlds. It suggests that reality is not a static block, but a dynamic story. Our universe began in a state devoid of structure, grew into a vast living tapestry, and will either continue to expand and evolve in complexity for some time, or eventually simplify again into quiescence. We got to observe a rich segment of that timeline, full of galaxies and life. That realization can fill one with a sense of reverence, not in a religious sense, but a profound respect for the majesty of nature. As our journey through the cosmos comes to an end, let's reflect on where we are. A small planet orbiting a medium star, on the edge of a galaxy that has at least 100 billion siblings, in a universe of maybe 2 trillion galaxies within our view, each brimming with stars and possibilities, all governed by the same physical laws, all born together in the same primordial explosion, all fated to either drift apart forever or perhaps crash together in some finale. We, ephemeral yet remarkable, stand here and through ingenuity have uncovered this story. It is a continuous, cinematic, emotionally resonant story, one that stretches from the beginning of time to the very ends of imagination. It's a story told by starlight and cosmic background whispers, written in equations and in the awe of anyone who looks up at the midnight sky. It's the story of the cosmos, our story. And though this particular telling of it must now conclude, the story itself goes on, written in the galaxies overhead and the atoms within us. As long as there are thinking beings to wonder and explore, the narrative will be retold, refined and cherished anew. In that sense, the cosmic story truly has no end. It lives so long as curiosity lives. So take a moment to step outside on a clear night. Feel the cool air. Look up. The light hitting your eyes has traversed the universe to reach you. The atoms in your body resonate with the history of the cosmos. The void may be vast, but you carry within you a universe of understanding that fills it with meaning. In the silence of the night, you can hear, if you listen closely, the echoes of the Big Bang and the songs of ancient starlight. The story of everything is speaking, and through our minds and hearts, the cosmos is listening to its own tale. In that communion, between the cosmos and our consciousness, lies a profound truth, that we are not apart from the universe. We are the universe, in small but significant part, and its fate and our fate are intertwined. From nothing we came, into nothing, or something beyond, we may go. But in between, we have the chance to witness and marvel at the grandest of spectacles, existence itself. Let us be grateful for that chance. Let us keep the cosmic perspective, allowing it to illuminate our lives with both humility and wonder. And let us continue the journey, always, for as far as mind and imagination can reach, embracing the mystery and majesty of the cosmos. The cosmic saga continues, and we are fortunate narrators within it. The final line is not yet written. Cosmos. The word itself is like a soft whisper in the dark of night, inviting us to look up and wonder. Born from ancient Greek, it means order or ornament, the opposite of chaos, the adornment of the night sky. For as long as humans have had language, we have given a name to the grand scheme of everything. We have always stood under the starry vault, hearts beating with curiosity, minds aching to understand what it all means. In a silent desert or on a grassy hill, our ancestors gazed at the stars with awe. Tiny lights flickering in the vast darkness became stories, became gods and guides. Under that cosmic canopy, they felt small yet connected to something immense. They sensed in those pinpoints of light a pattern, a rhythm, seasons changing, moons waxing and waning, a cosmos moving with purpose. To say cosmos is to imply the universe is not a random scattering of matter, but a harmonious whole. Beyond the chaos of daily life lies a greater order we can barely fathom. When we whisper the word, we summon an ancient feeling, the awe of knowing we are part of a mysterious, breathing entirety. The cosmos has always beckoned us. It humbles us with its scale and age, yet it also comforts us with the idea that we belong to it. We have wondered if the twinkling lights had messages for us, if the sky was a story written in stars. Generation after generation, we pass down myths and measurements, trying to bring the heavens into human understanding. Through wonder and imagination, we wove ourselves into the fabric of the cosmos. Even now, in an age of bright cities and glowing screens, that old impulse remains. Go somewhere dark and clear, and look up. The same Milky Way that dazed our ancestors arches overhead. In that band of light, millions of distant suns blurred together, we find both our history and our destiny. We feel the tug of an ancient question with each breath under the stars. What is all this? What does it mean that we live in a cosmos so vast and beautiful? From the earliest times, cosmos has meant more than just the physical universe. It carries a sense of profound order and connection. To reflect on the cosmos is to step beyond oneself, to see life on Earth as part of a larger story. It is to realize that the atoms in our bodies were born in stars, that our existence is tied to cosmic events beyond memory. It is to feel both tiny and tremendous, a fleeting moment and an integral part of eternity. So let us meditate on that word and all it entails. Let us journey outward and backward, upward and inward. In this story of the cosmos, we will travel from ancient myths to modern science. We will seek patterns in the sky that guided our ancestors and follow the light of distant galaxies that reveal our cosmic origins. We will ponder forces unseen and marvel at galaxies strung like jewels on invisible threads. Through it all, we hold on to that childlike wonder that first taught us to say cosmos with reverence. Our voyage begins where it must, in the tales and dreams of those who first looked up and tried to understand. The cosmos has always been our mirror and our muse. In its vastness, we have found grand myths of creation, of gods and monsters, of order emerging from chaos. To truly know the cosmos, we start with the ancient stories written not on paper, but across the sky itself. The ancient cosmos. Before science, there were stories. In the cradle of civilization, human beings looked to the sky and saw a grand drama unfolding above. The cycle of night and day, the march of seasons, the wandering of planets among the stars. All these celestial motions cried out for explanation. And so our ancestors gave the cosmos a face, a script, a meaning. The ancient heavens became a mirror of life on earth, a canvas on which they painted their hopes and fears. In ancient Egypt, each sunrise was not just a new day, but a victory of order over darkness. The sun was the god Ra, sailing across the sky in his brilliant boat. Every morning he was reborn in the east, bringing light and life. Every evening he descended into the underworld, battling forces of chaos to ensure the sun would rise again. To the Egyptians, the cosmos was upheld by these divine cycles. Ra's daily journey affirmed the rhythm of life, death, and renewal. The Nile would flood and recede, crops would grow and be harvested, just as surely as the sun would set and rise. Their myths gave cosmic meaning to earthly patterns, reassuring them that the universe was orderly and life-sustaining as long as the gods maintained balance. Far to the north, under Greek skies, people also sought cosmic order through myth. They imagined the night as a storybook opened overhead. Constellations were characters, a great hunter forever chasing a bull across the heavens, a hero carrying the weight of the sky on his shoulders, a queen enthroned among the stars. The Greeks looked up and saw legends. Orion with his shining belt of 3 stars, majestic and bold, the Great Bear lumbering around the North Pole, Andromeda chained to her stellar rock. Each constellation marked a tale of love or bravery or caution, a lesson twinkling from the firmament. Above all reigned Zeus, king of the gods, whose authority extended over both the sky and human affairs. The moving planets, the wanderers, were given names and personalities: fiery Ares, Mars; bright Aphrodite, Venus. By telling these tales, the Greeks found patterns in the stars, a cosmic order reflecting their own virtues and vices. The movement of the heavens hinted at divine plans. If Mars appeared red and bright, was Ares signaling war? If Venus rose in the evening, did Aphrodite bless lovers? In this ancient cosmos, the boundary between heaven and earth was thin, each influencing the other. Across the ocean in other lands, countless cultures wove their own cosmic tapestries. In old China, the night sky was envisioned as a celestial empire mirroring the earthly one. The emperor was said to be the son of heaven, and the stars were arranged into palaces and provinces. The Chinese sky was divided into constellations, forming a meticulous heavenly bureaucracy. A comet streaking through the sky might be interpreted as a wayward official or a portent of change in the kingdom. An eclipse was not just an astronomical event, but a dragon devouring the sun or moon, a sign that the harmony of the cosmos had been disrupted. To restore balance, people gathered to beat drums and gongs, scaring the dragon away. When the sun returned, it reaffirmed the cosmic order and the emperor's mandate. Through such rituals and myths, the ancient Chinese made sense of celestial motions as reflections of moral and political order on Earth. In the Indian subcontinent, sages imagined a layered cosmos teeming with gods and avatars. The sky was the abode of deities riding the clouds. The sun was Surya, a radiant god who drove his chariot across the heavens, pulled by 7 horses, the colors of sunlight. The moon was Chandra, gentle and cool, gliding through the night. The planets were also gods, each with personality and power, collectively called the Navagraha. Indian cosmology spoke of a universe born from a cosmic egg, of endless cycles of creation and dissolution, measured in kalpas, lasting billions of years, staggering spans of time encoded in myth. Yet these huge cycles tied into everyday life. The positions of planets could influence a person's destiny, the timing of rituals, the fortunes of kings. By observing the heavens, ancient Indians felt they could glimpse the divine rhythm that underpins reality, aligning their lives to the dance of the cosmos. No matter where on Earth, early peoples found ways to map the sky onto their own experience. The Babylonians meticulously tracked the movements of planets and stars, and wove them into their myths of gods like Ishtar, Venus, and Marduk, Jupiter. They recorded eclipses and believed in cosmic omens, that a falling star could foretell the fall of a king. The Maya of Central America built observatories to follow the sun and Venus, timing agriculture and ceremonies to celestial cycles. For them, the cosmos was a ceaseless wheel of time, with each era ruled by different gods. Indigenous peoples of North America saw constellations as great hunters and animals, integrating the sky into storytelling and navigation. Every culture found its own cosmic North Star by which to guide human life. These ancient cosmologies differed in detail, but they shared a purpose: to make the vast, unknowable sky intimate and meaningful. By projecting stories onto the stars, our ancestors found comfort and guidance. The cosmos became a grand clock and calendar, its motions providing a sense of predictability in an uncertain world. The rising of Sirius just before dawn signaled the Nile's flood, and thus renewal, to the Egyptians. The appearance of the Pleiades in spring told Greek sailors that sailing season had arrived. The heavens and earth were interwoven in a tapestry of sign and story. Most importantly, the ancient myths gave people a sense of belonging in a huge universe. If the heavens were populated by gods and heroes, then human life was part of that divine drama. Nothing was random. The cosmos had intention, personality, narrative. A shooting star could be a departing soul. The Milky Way could be the spilled milk of a goddess or the bridge to the afterlife. By aligning with these cosmic stories, performing rituals at solstices, building temples to face sunrise, tracing the planet's paths, ancient humans felt they were participants in the cosmos, not mere spectators. In those early nights under open skies, the cosmos was both guide and canvas. People drew connections between the circling stars and the cycles of their own lives. Birth, death, love, conflict, harvest and drought, all found reflection in the movements above. The myths may not have been scientifically accurate, but they were true in a deeper sense. They captured the emotional truth of being human in a vast and mysterious universe. They helped us navigate not just by land or sea, but through the uncharted waters of existence. Thus, the ancient cosmos was a place of narrative and meaning. It was alive with motion and intention. Every sunrise was a story, every eclipse a warning or wonder, every constellation a reminder that we are part of something greater. With these stories, humanity's long conversation with the stars began. Over millennia, those conversations led to patterns noted, calculations made, and the first whispers of a new approach to understanding the cosmos. Myth would eventually inspire measurement, and storytelling would lead to science. As our methods changed, the goal remained the same: to find our place in the grand order of the cosmos, and to ensure that the cosmos made sense. The birth of the modern cosmos. For thousands of years, the Earth sat proudly at the center of the known universe in human imagination. It seemed obvious. The ground beneath us felt still and solid, while the heavens whirled around. The sun rose in the east, journeyed overhead, and set in the west, surely circling us. The stars rotated nightly around the North Star, as if painted on the inside of a celestial dome with Earth at its core. This geocentric cosmos, codified by philosophers like Aristotle and Ptolemy, was cozy and reassuring. Humanity lived at the heart of creation, the focal point of God's plan or nature's design. Above, the crystal spheres turned in orderly concentric circles, carrying the sun, moon, planets, and stars in divine choreography. In this model, the cosmos was finite, well-ordered, and centered on us. But whispers of a different truth had long existed. As early as ancient Greece, a few bold thinkers, like Aristarchus, suggested that the Earth might move around the sun, This idea was largely dismissed or forgotten for centuries. It simply felt wrong. How could Earth be moving? We felt no incessant wind from such motion, no constant shaking. And if Earth swung around the sun, where was the parallax in the stars? The tiny shift in star positions that such motion should produce? None could be seen with the naked eye. So the geocentric view held sway through antiquity and the Middle Ages. Then, in the 16th century, a Polish astronomer named Nicholas Copernicus quietly revolutionized our view of the cosmos. He proposed a bold simplification. Suppose the sun is at the center, and the Earth is just another planet circling it. In one stroke, the cosmic order could be explained more elegantly. The retrograde loops of Mars in the sky, the cycles of Venus, all made sense if Earth was moving too. Copernicus published his heliocentric theory in 1543, carefully dedicating it to the Pope and couching it as a mathematical convenience. Yet the implication was clear. Our planet was not the pivot of creation. It was a radical leap, met with skepticism or silence by most contemporaries. After all, it upended common sense and challenged religious doctrine. But the seed of the modern cosmos was planted. It would take brave observers and thinkers to make that seed sprout. Early in the 17th century, Galileo Galilei in Italy heard of a new invention, the telescope. He crafted his own and pointed it at the night sky, becoming the first human to see certain wonders. Through Galileo's telescope, the moon revealed mountains and craters. Not the perfect heavenly orb philosophers imagined. Jupiter appeared as a tiny disk, accompanied by 4 points of light that moved, Jupiter's moons, orbiting not Earth but Jupiter itself. It was a celestial ballet defying geocentric dogma. Here were objects clearly circling a world other than our own. Galileo also observed Venus showing phases like the moon, a behavior only possible if Venus circled the sun, not Earth. Star clusters in the Milky Way resolved into countless faint stars, suggesting the cosmos was far larger and richer than assumed. With each observation, Galileo dealt blow after blow to the Earth-centered model. He wrote of his findings, championing the Copernican sun-centered system. This earned him admiration among some and condemnation from others. The idea that Earth moved was still too great a heresy for many. Galileo famously faced the Roman Inquisition and was forced to recant. But the truth was out. Our world was not the fixed center. Earth was a planet in the heavens, one among several. With the heliocentric model gaining evidence, the cosmic stage expanded. Johannes Kepler refined the picture by discovering that planets travel in ellipses, not perfect circles, and speed up and slow down in their orbits according to precise laws. It was as if the cosmos had its own music, and Kepler had begun to hear its rhythm in the data. Shortly after, Isaac Newton in England provided the masterstroke. He formulated the law of universal gravitation, showing that the same force pulling an apple to the ground keeps the moon circling Earth and Earth circling the sun. In Newton's new universe, the celestial and terrestrial were unified. The heavens were not held up by crystal spheres or angelic powers, but by gravity, an invisible thread binding planets to stars. Suddenly, the cosmos became a mechanistic marvel, a grand clockwork governed by laws that could be understood and even predicted by humans. The music of the spheres was transcribed into mathematics. The modern scientific cosmos was being born, and in it, Earth was merely one cog in a vast machine. As the centuries turned, our understanding leapt forward. By the 19th century, astronomers realized the sun itself was not the center of all creation, but rather the center of a local family of planets. The stars, once thought to be distant lanterns or holes in the firmament, were confirmed to be other suns scattered across unimaginable distances. The night sky, which to the ancients was a fixed dome, became an ocean of stars in 3 dimensions. We measured the first distances to stars and found them stupefyingly far. The nearest, Alpha Centauri, is over 4 light-years away, 40 trillion kilometers. The absence of observed parallax now made sense. The stars were vastly farther than imagined in Aristotle's time, so their parallax was tiny. Our Sun was thus not the center of all stars, but just one star drifting in a great starry city. That starry city is the Milky Way galaxy, a broad band of light wrapping the sky. In the early 20th century, astronomers pieced together that the Milky Way was an immense disk of hundreds of billions of stars. Our Sun lay not at the center of this disk, but off to the side in a spiral arm, a suburban star in the galaxy's outskirts. We had been demoted once again from center of the universe to mere resident of one galaxy among possibly many. Yet even then, many believed the Milky Way was the entirety of the universe, an island universe surrounded by a void. Reality had another plot twist in store. In 1920, astronomers Shapley and Curtis engaged in the great debate over the scale of the universe, arguing whether spiral nebulae, like Andromeda, were part of the Milky Way or distant galaxies of their own. This question was settled in the mid-1920s when Edwin Hubble, using the giant Mount Wilson telescope, observed stars in the Andromeda Nebula. He identified particular stars called Cepheid variables, whose blinking rhythm allowed him to calculate their distance. The result was staggering. Andromeda was far outside our Milky Way, a galaxy in its own right. In one announcement, Hubble shattered the confines of our known cosmos. The universe was vastly larger than we had imagined. The Milky Way was but one galaxy among billions spread throughout space. As if that weren't enough, Hubble soon discovered that these galaxies are flying apart from each other. Space itself is stretching. The spectra of distant galaxies were shifted toward the red, like the lowered pitch of a receding siren, indicating they were rushing away. The farther the galaxy, the faster it fled. It was as though the cosmic fabric were inflating, carrying galaxies apart like driftwood on a rising tide. The implication was profound. If you rewind this expansion, there was a time when everything was closer together, perhaps a moment when the entire universe was a single point. The static, eternal cosmos of old gave way to a cosmos with a dynamic history, a beginning, what we now call the Big Bang, and perhaps an end. Thus, in just a few centuries, our cosmic understanding transformed utterly. We went from a cozy Earth-centered bowl of stars to an immense, law-governed expanse where Earth is a moving planet, the Sun a modest star, the Milky Way one galaxy among a multitude, and the universe itself expanding and evolving. Each step was a blow to human vanity, but a boon to human knowledge. With each step, the cosmos grew grander and more mysterious, yet also more knowable through science. The modern cosmos was not built in a day. It emerged gradually as old theories shattered and new discoveries took their place. It required curiosity, courage, and the willingness to accept that our intuitions can be wrong, that reality may be far stranger and more magnificent than our ancestors ever dreamed. By embracing a sun-centered system, by mapping the Milky Way, by discovering galaxies beyond our own, humanity experienced a kind of cosmic rebirth. We shed ancient illusions and stepped into a wider universe, guided by observation and reason. And as the scale of the cosmos expanded, so did our sense of wonder. The night sky, once a fixed storybook of constellations, became an endless frontier. We now knew that when we gaze at the Milky Way, we peer into the heart of our galaxy, and when we spot the faint smudge of Andromeda, we behold a sister galaxy 2.5 million light-years away. The light entering our eyes left that galaxy before our species existed. The modern cosmos is vast, full of galaxies drifting in the darkness, all governed by the same natural laws. This was a cosmos that could be analyzed with telescopes and equations, but it still evoked awe. In fact, the more we discovered, the more profound and humbling the mystery became. Having found our true place, not the center, but part of a cosmic community of worlds, we were ready to explore what this newfound universe looked like. With minds freed from the confines of geocentrism, and with ever more powerful tools, we set out to observe the cosmos in all its glory. The next step of our journey would be to truly behold the universe with new eyes, to collect the ancient light of stars and galaxies, and from it, read the story of time itself. The observable cosmos. Armed with newfound knowledge and powerful eyes, humanity set out to truly see the cosmos. What had been mysterious points of light became tangible suns and galaxies through the lens of the telescope. Our curiosity, once limited by human sight, now leapt forward with each improvement in our instruments. The cosmos opened like a book under a magnifying glass, revealing detail upon detail written in light. We learned a startling fact. To observe the universe is to look back in time, for light takes time to travel. Consider the starlight reaching us tonight. The nearest star beyond our sun, Proxima Centauri, lies 4.24 light-years away. The light hitting our eyes from that star left it over 4 years ago, crossing trillions of kilometers of space before gently landing on our retina. We see Proxima Centauri not as it is now, but as it was 4 years in the past. And that's our nearest neighbor. Sirius, the brightest nighttime star, shines 8.6 light-years away. We see it as it was about when the last decade began. The North Star, Polaris, is 433 light-years distant, so the light-guiding sailors tonight set off around the time Galileo first pointed a telescope skyward. With every step up in distance, we peer further back in time. The Andromeda Galaxy, faintly visible as a smudge, is over 2 million light-years away. When its light began its journey, early hominins on Earth were chipping stone tools. This realization transformed the night sky into a kind of cosmic history book. Telescopes became our time machines, collecting ancient photons that have been traveling for eons. By capturing this light and studying it, we decode stories from long ago and far away. The color and brightness of a star's light tells us its composition and temperature. The Doppler shift of a galaxy's light reveals its motion through space. When we see the glittering band of the Milky Way, we now understand it as the combined glow of billions of stars, many whose light has traveled tens of thousands of years to reach us. To look out is to look back. As telescopes grew in size and sophistication, the depths of the observable cosmos unfolded. In the 19th century, astronomers with new refractors and reflectors saw that some fuzzy patches of light, nebulae, had spiral shapes. They suspected these might be island universes, galaxies outside our own, later confirmed by Hubble. Each advance in observational power was like opening a new window in our cosmic house, offering a view further into space, and thus further into the past. In the 20th century, we launched telescopes above the blurring veil of Earth's atmosphere. The Hubble Space Telescope, deployed in 1990, proved transformative. Free from atmospheric distortion, Hubble could stare deeper into space than any instrument before. In 1995, astronomers did a daring experiment. They pointed Hubble at a seemingly empty, dark patch of sky near the Big Dipper, where no known stars or galaxies were visible, a speck of sky no bigger than a grain of sand held at arm's length. They let Hubble's camera soak in light for 10 straight days. What came back was a revelation. The now famous Hubble Deep Field image. Far from empty, that little patch of darkness was overflowing with nearly 3,000 galaxies, of all shapes, sizes, and colors, each a swarm of billions of stars. Some were relatively nearby, but many were incredibly distant, their light having traveled for billions of years. In those dim smudges, Hubble had captured galaxies as they were when the universe was young, cosmic baby pictures, just a few billion years after the Big Bang. That single image was like a core sample of the universe, drilling down through cosmic time. It showed a universe teeming with galaxies, even in a tiny, unremarkable bit of sky. Later, Hubble gazed even longer and deeper, producing the ultra-deep field in 2004, and then the extreme deep field in 2012, revealing galaxies more than 13 billion years in the past, when the first galaxies were just emerging. In the Hubble ultra-deep field, almost every point of light is an entire galaxy. Some are seen as they were only 400–800 million years after the Big Bang, full of newborn stars. By looking far away, we looked back to a time when the universe was young. Every telescope, whether a backyard amateur's or a great observatory in space, is fundamentally a light collector. It gathers the sparse, ancient photons that rain down on us, focusing them into an image or feeding them to instruments that can analyze their secrets. Through visible light telescopes, we see stars and galaxies as our eyes would, only fainter and farther. Through radio telescopes, we tune in to the whisper of the cosmos at long wavelengths, the songs of cold hydrogen clouds and the ghostly crackle of remnant radiation from the Big Bang. Infrared telescopes peer through cosmic dust to find stars being born in swaddling nebulae and detect the faint glow of the most distant galaxies, whose light has been stretched to infrared by the expanding universe. Ultraviolet and X-ray telescopes capture high-energy phenomena, flares on stars, the glow of gas around black holes, the hot plasma in galaxy clusters. Each portion of the electromagnetic spectrum is like a different chapter of the cosmic story, and we've learned to read them all. The observable cosmos extends far beyond what human eyes alone can see, thanks to these extensions of our senses. Perhaps the most ancient light of all that we have observed is the cosmic microwave background, the cooled, faint afterglow of the Big Bang itself. Discovered by accident in 1965 as a pervasive microwave hiss in a radio antenna, this all-sky glow is the light from about 380,000 years after the Big Bang, when the hot plasma of the early universe finally cooled enough to become transparent and release photons in all directions. We see it now as a uniform microwave glow coming from every direction, just a few degrees above absolute zero, the oldest fossil of light, nearly 13.8 billion years old. Detailed maps of the microwave background made by satellites, COBE, WMAP, Planck, show it's mostly uniform but with tiny variations in temperature, the seeds of all future cosmic structure. This is literally a baby picture of the universe, long before stars or galaxies existed. It's a reminder that our telescopes have pushed our vision to its limit. We can nearly see the Big Bang itself. Within the observable cosmos, we have catalogued wonders beyond count. We've seen star clusters with hundreds of thousands of suns, nebulae that are stellar nurseries sculpted by winds and radiation, galaxies colliding and merging in dances that last hundreds of millions of years. We have detected planets around other stars by the subtle dimming of starlight or the wobble of spectral lines. We now know planets are common, numbering in the billions in our galaxy alone, from hot Jupiters skimming their stars to Earth-like rocks in temperate orbits. We've measured the universe's expansion and even glimpsed its acceleration due to an enigmatic, dark energy. All of these achievements flow from extending our senses with instruments and collecting the light, or other radiation, that streams through space, carrying messages from afar. Telescopes, in a poetic sense, gave the universe a voice in time. Through them, we listen to the echoes of the past. When we look at a distant galaxy cluster, we might be seeing it as it was when our own sun had not yet formed. In the faint glow of a red-shifted galaxy, we might be witnessing an event that occurred shortly after the dawn of time. The observable cosmos is a time capsule cosmos. The phrase observable universe also reminds us of limits. Light from extremely distant regions hasn't had time to reach us in the 13.8 billion years since the Big Bang, so there are horizons we cannot see beyond, at least not yet and maybe not ever, if the expansion accelerates. This doesn't mean those regions don't exist, just that they lie beyond our view. So the observable cosmos, everything we can see or detect, is still potentially only a piece of a larger whole. But it is grand enough, about 93 billion light-years across today, accounting for expansion, containing perhaps 2 trillion galaxies. Each of those galaxies, in turn, contains billions or trillions of stars, and around many of those stars orbit worlds we are only beginning to discover. Looking up from Earth, a small creature on a small planet, we now can perceive structures and events on scales our ancestors never imagined. We have essentially pulled back the curtain of distance, and what we found is a universe that is dynamic and changing. The sky is no longer a fixed backdrop, it is a living history. Every point of light is a story unfolding. Some star being born in a nebula, another nearing its death as a red giant, a galaxy swirling in a gravitational dance with a neighbor, a supernova shining briefly like a cosmic firework. We catch these events mid-stride, like reading random pages from a vast novel. Telescopes allowed us to no longer be passive inhabitants of the cosmos, but active witnesses to its grand story. Each night an observatory opens its dome and points its giant eye outward. We extend our reach farther in space and further back in time. We do this not for conquest, but for understanding, to fill in the chapters of the cosmic story from the beginning until now. And through these observations, we have come to see the universe not as static, but as an unfolding tale with a beginning, middle, and ongoing narrative. Having surveyed what we can see, the stars and galaxies and background glow, we noticed a grand pattern in how matter is arranged on the largest scales. Galaxies are not scattered randomly. They form a vast cosmic web of filaments and voids. To this we now turn, the large-scale structure of the universe, the cosmic web that gravity built, seeded by tiny quantum ripples from the dawn of time. The cosmic web. On the grandest scales, the universe is organized into a vast cosmic web, a structure both simple and intricate, like lace stretching across unimaginable distances. If we could zoom way, way out beyond our galaxy, clusters of galaxies would begin to outline a pattern. Galaxies are not evenly sprinkled through space, but collected in filaments, sheets, and dense knots, clusters, with huge voids between them where few galaxies reside. The cosmos, viewed from afar, resembles a web or sponge, bright threads and nodes of matter surrounding dark, empty bubbles. Gravity is the master architect of this cosmic web. Over billions of years, gravity drew matter together, amplifying tiny primordial irregularities into the vast structures we see now. In the early universe, matter was nearly uniform, with slight denser spots here and there, imprinted as those tiny temperature ripples in the cosmic microwave background. As the universe expanded and cooled, these denser spots, seeded by quantum fluctuations and stretched by inflation, exerted a bit more gravitational pull, drawing in surrounding gas and dark matter. Over time, the slightly denser regions grew into filaments and clumps. The empty regions gave up matter to the crowded ones and became enormous voids. Imagine flying through a slice of the universe a few billion light-years across. For millions of light-years, you might see almost nothing, traversing a void where only the occasional dim galaxy or wisp of hydrogen appears. Then, ahead, you'd see a filamental chain of galaxies stretching across space like a gossamer strand. Drawing closer, that filament resolves. It's a chain of galaxy clusters connected by thinner tendrils of galaxies. You follow the filament to a nexus, a rich cluster of galaxies where filaments intersect, perhaps like the Coma cluster, containing thousands of galaxies swarming around a common center. From that hub, multiple filaments radiate out, each leading to other clusters. This is the cosmic web, clusters, nodes, connected by filaments, separated by voids. It's akin to the structure of a sponge or foam, an interlocking network of walls and channels. Our own Milky Way lies within this web. It is part of a small cluster, the local group, which in turn is on the outskirts of a larger Virgo cluster. That cluster is part of a filament that stretches toward the Great Coma cluster. In fact, astronomers have mapped our local section of the cosmic web and found that our local group, Virgo cluster, and other nearby clusters are all part of a supercluster system they've named Laniakea, Hawaiian for immeasurable heaven. Gravity is drawing our local group, including the Milky Way and Andromeda, toward the Virgo cluster, and all of Virgo and its neighbors toward an even larger concentration called the Great Attractor. Our galaxy, in the far future, will drift along the web into those larger structures, though perhaps not before dark energy's expansion halts that motion, an evolving contest between expansion and gravity. One of the striking things about the cosmic web is how empty the voids are. Some voids span hundreds of millions of light years with almost no galaxies. In contrast, the filaments and clusters are crowded. In massive clusters, galaxies can be just tens of thousands of light years apart, very close in cosmic terms, and space between them is filled with hot, X-ray emitting gas, heated by the gravity of the cluster. The filaments themselves contain not just the galaxies we see, but also lots of dark matter and diffuse gas connecting cluster to cluster. In fact, simulations and observations suggest that most of the ordinary matter, atoms in the universe, resides not in galaxies, but in the filamentary tendrils of warm, hot intergalactic medium, WIM, threading the voids. It's like an invisible scaffold. The galaxies are like dewdrops on a spider web, outlining it, but much of the web itself is faint and hard to see directly, composed of thin gas and especially dark matter. Dark matter, that mysterious substance making up about 85% of the matter in the universe, is the backbone of the cosmic web. While ordinary gas can radiate energy and settle, dark matter does not radiate, so it forms large, diffuse halos. It was dark matter that first clumped due to gravity, with ordinary matter later falling into the gravitational wells the dark matter created. In supercomputer simulations of cosmic structure formation, one starts with a nearly uniform distribution of dark matter, with tiny random density fluctuations, and lets gravity work over billions of years. The result is a filamentary network, extremely similar to what large galaxy surveys observe. The bright nodes in such simulations correspond to where clusters of dark matter, and later galaxies, form. The long dark strands correspond to filaments of dark matter along which galaxies and clusters align. The empty regions correspond to voids evacuated of matter. It's a beautiful example of emergent order. Out of near uniformity emerges complexity, a cosmic web, simply from the action of gravity over time. Tiny fluctuations in density, originating from quantum jitters in the infant universe, became the template for everything. Stars, galaxies, clusters, the web. The cosmic web is the largest pattern we know. It shows that on the grandest scales, the universe has a structure, homogeneous and isotropic, only when averaged over truly enormous volumes, but locally clumpy in a sponge-like way. It's often said that the universe on very large scales looks the same everywhere, the cosmological principle. And it's true that if you average over hundreds of millions of light years, one region is much like another in terms of galaxy counts. But zoom in a little less and the web stands out. Homogeneous only in a statistical sense, but in reality, threaded and bubbled. It's intriguing to note parallels between the cosmic web and other networks. The distribution of matter in the universe, as revealed by galaxy surveys like the Sloan Digital Sky Survey, bears a resemblance to the neural networks in brains, or the large-scale structure of the internet, hubs and spokes, clustering of connections. This might just be a coincidence of pattern. Nature finds similar solutions to connectivity problems, or possibly a hint of deep universal principles of self-organization. When scientists compared the network properties of the cosmic web and the network of neurons in a brain, They found tantalizingly similar complexity and distribution despite the difference in scale by 27 orders of magnitude. It's a reminder that simple laws, like gravity's inverse square attraction and expansion of space, can create intricate structures mirrored elsewhere in nature. Crucially, the cosmic web is not static. It's still evolving. Over time, gravity will continue pulling matter along filaments into clusters. The rich get richer, clusters accumulate mass, and the voids get emptier. Superclusters may merge into even larger structures, sometimes called hyperclusters, though there's a limit. Eventually, dark energy's accelerated expansion will push galaxies away from each other faster than gravity can overcome. It's thought that in the far future, 100 billion years or more, distant clusters will recede beyond our observable horizon, effectively isolating each remaining cluster or group as its own island universe. At that point, any cosmic web structure beyond our local cluster will be unobservable. The larger pattern will be lost to view, though it will still exist beyond our reach. For now, however, we live at a time where we can map the cosmic web, see its glory, and use it to test our theories of cosmology. Understanding the cosmic web helps answer profound questions. How did the universe transition from the near-uniform fireball after the Big Bang to the rich hierarchy of structure we see now? The answer: the interplay of gravity, pulling matter into structure, and expansion, spreading things out, created a foam-like arrangement. Tiny fluctuations grew to filaments, matter flowed like rivers into cluster basins, and vast quiet voids were left where nothing much happens. Having journeyed from our planet to the galaxy, to clusters and the cosmic web, we've framed the large-scale architecture of the cosmos. But what holds this architecture together? And what threads run through every level of this tapestry? For that, we must discuss the fundamental forces and fields: gravity, electromagnetism, and the nuclear forces, the hidden framework, underlying movement and structure everywhere in the cosmos. Forces and fields. In the grand ballet of the cosmos, 4 fundamental forces choreograph every move. They are the unseen influences that shape everything from the orbits of planets to the light in our lamps to the fusion in stars. Though invisible, they form a hidden framework that makes the universe dance. Each force is like a different instrument in an orchestra, and together they compose the music of the cosmos, from the smallest scales to the largest. Gravity is the most familiar, and yet in many ways, the most mysterious. It is the sculptor of the cosmos, the gentle but persistent pull that guided matter into spheres and orbits. Every time an apple falls from a tree, or we feel our own weight, we are feeling gravity. This same force reaches across the emptiness of space to keep the moon circling Earth and Earth circling the sun. It binds solar systems and steers stars around the centers of galaxies. It gathered galaxies into clusters along the cosmic web. Gravity is by far the weakest of the 4 forces on small scales. A tiny magnet can lift a paperclip against the entire Earth's gravity. But over large scales it dominates because it only attracts and never cancels out. Over time, its tiny tug accumulates into an inexorable current that builds structure. Einstein revealed that gravity is not a force in the traditional sense, but a curvature of space-time itself. Mass and energy bend the fabric of space and time, and objects move along those curves. The sun dents space-time, and Earth rolls around that dent like a marble in a bowl. This elegant understanding tells us gravity is the shape of the cosmos's geometry. It's what gives the universe its large-scale structure, what makes a cloud of gas collapse into a star, what pins us to our beloved Earth. Gravity is both patient and powerful. Given enough time, it can gather raw matter into galaxies or crush a star into a black hole. Largely, though, gravity is the quiet, persistent heartbeat of the cosmos, keeping worlds in their courses and the celestial architecture intact. Electromagnetism is the artist and communicator of the universe. It is the force responsible for light itself. Every beam of starlight traveling to our eyes is an electromagnetic wave. It also binds atoms and molecules. It's the reason you do not fall through the floor. The electrons in your shoes repel the electrons in the floor. Electromagnetism is vastly stronger than gravity at small scales. It's what makes magnets cling and lightning crackle, what lets compasses point north and radio waves carry music. In atoms, the electromagnetic force binds negatively charged electrons to positively charged nuclei, forming atoms. It causes atoms to link into molecules by sharing electrons, giving us the variety of chemistry. The warmth you feel from sunlight, the colors of a rainbow, the glow of a distant galaxy, all delivered by electromagnetic radiation. Unlike gravity, which only pulls, electromagnetism can both attract and repel. Opposite charges attract, like charges repel. This push-pull interplay creates structure on the atomic and human scales. It keeps electrons whizzing around nuclei instead of flying away, and it causes molecules to have the shapes they do, enabling the complex chemistry of life. In the cosmos, electromagnetism governs the behavior of plasma, the hot, charged gas found in stars and nebulae. It sculpts the beautiful filaments of glowing gas in nebulae and the majestic arcs of solar flares rising from the sun. When we see the auroras dancing near Earth's poles, that's electromagnetism at play. Charged particles from the sun, guided by Earth's magnetic field into the upper atmosphere, causing molecules to glow. Electromagnetic fields fill space around planets and stars. For instance, the sun's magnetic field, carried by the solar wind, creates a protective heliosphere around our solar system. On Earth, the electromagnetic force is the foundation of technology, electricity, electronics, wireless signals, and biology, chemical bonds, nerve impulses. In a cosmic sense, if gravity is the weaver of the cosmic tapestry, electromagnetism provides the vibrant colors and textures. It gives matter structure and allows the universe to be visible and radiant. The strong nuclear force is the powerful glue of the atomic nucleus. Working at tiny scales, the size of an atomic nucleus or smaller, it binds protons and neutrons together despite the electromagnetic force trying to push positively charged protons apart. Protons naturally repel each other strongly, since like charges repel, and within a nucleus, they are extremely close. It is the strong force that acts like cement to hold these protons and neutrons tightly bound. It is the strongest of the four forces in terms of raw strength, but it operates only across minuscule distances, about the diameter of a proton. Beyond that, its influence drops virtually to zero. Think of it as Velcro that sticks only at very close range. This is fortunate. If the strong force had longer reach, every atom might glom together into one giant nucleus. If it were weaker, nuclei heavier than hydrogen, which contain multiple protons, would fly apart, and the diversity of elements would vanish. In the cores of stars, when temperatures and pressures slam protons together with tremendous force, the strong force takes hold and fuses them. Hydrogen nuclei merge into helium, releasing tremendous energy. This nuclear fusion, governed by the strong force overcoming electromagnetic repulsion, is what makes stars shine for billions of years, converting a bit of mass to energy via EXMC2. The sunlight that warms your face is a byproduct of the strong force at work in the sun's heart, forging helium and releasing energy. Later, in a massive star's life, the strong force will operate on heavier elements. Carbon fuses into heavier elements all the way up to iron. But iron is the end of the line. Fusing iron doesn't yield energy, so in the final moments of a massive star, when its core is iron, the outward pressure stops and gravity causes collapse. The core implodes until the strong force between nucleons, protons, neutrons, and quantum pressures of neutrons say no further, either halting collapse and producing a neutron star, or if the star is massive enough, even the strong force yields and a black hole forms. In either case, the star's outer layers explode in a supernova, scattering heavy elements into space. The strong force in those violent moments forged all elements heavier than iron, gold, uranium, etc., which seed future stars and planets. Thus, the strong force is the creator of elements. It stitched the carbon in your cells, the oxygen in your water, the iron in your blood. Aptly named, it is stronger than electromagnetism at short range, for it must be to bind the nucleus. But outside the nucleus, we never directly sense it. It's confined to the tiny atomic realm. It's the secret fire at the center of matter, unleashed only in rare moments like inside a star or a nuclear reactor or bomb. Without the strong force, atoms beyond hydrogen wouldn't hold together, and the cosmos would be a featureless fog of particles. With it, the richness of atomic matter exists. The weak nuclear force is the most subtle and elusive of the four. It operates within atomic nuclei as well, responsible for certain kinds of nuclear transformations. In particular, it governs radioactive decay and the conversion of one type of particle into another. The weak force is the force of change. Where the strong force holds nuclei together, the weak force lets them transmute. For example, the weak force can turn a neutron into a proton, an electron, and an antineutrino. This is beta decay. This happens in naturally radioactive elements, like a carbon-14 atom decaying into nitrogen-14, emitting an electron. It also happens in the sun. In the proton-proton fusion chain, two protons fuse, and one must turn into a neutron via the weak interaction, allowing them to form deuterium, heavy hydrogen. Without that step, the sun's primary fusion cycle would stall. Thus the weak force, though feeble, is crucial. It lights the stars by enabling fusion and shapes the decay of heavy elements that heat Earth's interior. Radioactive decays of uranium, thorium, potassium contribute to Earth's geothermal heat, driving plate tectonics and volcanoes. The weak force has an incredibly short range, even shorter than the strong force, and is aptly named. It's far weaker than electromagnetism and strong force, stronger than gravity on subatomic scales, but gravity is irrelevant there. We typically notice the weak force only through radioactive decays or in high-energy particle physics experiments. It's carried by heavy W and Z bosons. It doesn't create binding structures. Instead, it allows particles to change identity. It is unique in that it can change a quark's flavor, turning a down quark to an up quark or vice versa, which is how a neutron becomes a proton. We rarely sense the weak force in daily life. It's a behind-the-scenes presence, but it's essential for the evolving cosmos. Without it, the sun wouldn't shine the way it does, and many elements produced in supernovae wouldn't form, because beta decays during those explosions create elements like gold from lighter ones. If the strong force is the builder and electromagnetism the artist, the weak force is the quiet facilitator of change, enabling the cosmic alchemy that gives variety to matter. These four forces together form the infrastructure of reality. Each has its domain of influence. Gravity dominates the astronomical realm of planets, stars, and galaxies. Electromagnetism rules atoms, chemistry, and everyday phenomena. The strong force governs the atomic nucleus and powers stars. The weak force allows the transmutations that underlie both star power and natural radioactivity. They are the threads running through the cosmic fabric, and the fields they generate fill the space around us. Modern physics describes forces via fields and exchange particles. The gravitational field, possibly with gravitons. The electromagnetic field, carried by photons. The strong force field, carried by gluons binding quarks. The weak force field, carried by W and Z bosons. But leaving such technicalities aside, what's astonishing is that these few interactions explain a vast range of phenomena. Consider how these forces all play together in a simple moment. You stand outside on a sunny day. Gravity roots you to Earth and holds our planet in orbit around the sun. Electromagnetism governs the sunlight warming your face and lets your eyes see the world in color. It also keeps the ground solid beneath your feet, electrostatic repulsion between atoms. The strong force long ago fueled the nuclear reactions that produce that sunlight, and even now holds the nuclei of your atoms together. The weak force within the sun allowed protons to turn into neutrons, ensuring the fusion cycle could proceed steadily and power the sunlight. In your body, the weak force is causing a handful of potassium-40 atoms to decay each second, emitting neutrinos that stream harmlessly into space. In that one moment, all four forces are at work seamlessly, and you remain blissfully unaware, simply enjoying the warmth. Throughout cosmic history, these forces guided the formation of structure and the dynamics of change. Gravity drew together the cosmic web and formed stars and galaxies. Electromagnetism made those stars shine and binds atoms into molecules, leading to planets and life. Within stars, the strong and weak forces together forge new elements, which are then spread by supernovae to seed planets and life. We often call them forces of nature, but one might also call them cosmic rules or fundamental interactions, the basic ways pieces of the universe interact. Understanding these forces has allowed us to deepen our comprehension of the cosmos and harness aspects of it for our use. They also inspire a sense of marvel, how elegant that four simple interactions underlie the complexity of the entire universe. Gravity, shaping a galaxy cluster or light from a quasar, 12 billion light-years away, traveling to Hubble's mirror. It's all governed by the same physics that dictates an apple falling or a magnet sticking on a fridge. It suggests a profound unity that from the smallest scales of quarks to the largest scales of galaxy superclusters, the same fundamental forces operate, just with different relative strengths and effects. There are moments in modern physics where we dream of an even more unified picture. Perhaps these four forces were once one, a single force in the extremely hot young universe that later split into four distinct facets as the cosmos cooled. This is the idea behind grand unified theories and attempts to include gravity in quantum theory. Whether nature has such a unified force or not, what stands is that from the grandest cluster of galaxies down to the tiniest atomic nucleus, these four interactions suffice to explain what we observe. When you watch the stars at night, their light reaching you is an interplay of gravity, holding those stars together, and electromagnetism, bringing their light to your eyes, and even quantum effects of atoms, allowed by electromagnetic and strong forces. These forces are the invisible poetry of the cosmos. They make the silent emptiness of space a dynamic arena. Through them, a universe that could have been chaos becomes a symphony of structure and motion. As we understand these forces, we appreciate the finely tuned balance that allows complexity to emerge. With gravity alone, matter would clump infinitely, or not form structure if universe expands too fast. Without gravity, no stars or planets would gather. Without electromagnetism, no atoms or light. Without strong force, no nuclei beyond hydrogen. Without weak, no stellar alchemy creating diverse elements. Our cosmos manages to have them all in just the right mix to give rise to the rich tapestry we see, including us, observers who can reflect on it. Armed with knowledge of the forces, we can now tell the stories governed by them. The deep time tales of stars and galaxies, their births and deaths. These will be our next focus, to see how the cosmos changes over time, how stars live and die, how galaxies evolve, and what fate awaits the universe. Time is the stage on which the forces play. And entropy, the tendency toward disorder, provides an arrow to that time. Let us now unfold the saga of deep time, witnessing the life cycles of stars and the evolving cosmos, told not in equations, but in emotions, as we connect to these distant events that ultimately made our own existence possible. Deep time. In the vast ocean of time, stars are born and die like living things. Galaxies grow and change, and even black holes have life stories. To truly grasp the enormity of cosmic history, we must step outside the human sense of time and enter epochs that dwarf our imagination. Deep time is a realm where 1,000,000 years might pass in the blink of an eye, where the dance of creation and destruction unfolds over eons, with a grandeur at once awe-inspiring and poignant. The life of a star. Picture a dark nebula in a spiral arm of the Milky Way, a cold, dusty cloud light years across, quietly drifting for ages. Within it, a subtle gathering begins, perhaps the shockwave of an ancient supernova, or the pressure of a spiral density wave triggers parts of the cloud to contract under gravity. In those shrinking pockets, gas and dust draw together, atoms crowd and collide, heating up. What was cold and dark starts to glow dull red from the heat of compression. In one such cocoon, at the center of the collapsing cloud, a new light ignites. A protostar is born. It's like a baby star, unstable, convulsing with magnetic storms, gobbling up gas from the surrounding cloud. As it grows, its core becomes denser and hotter until one miraculous moment, hydrogen atoms, squeezed and heated fiercely, begin to fuse into helium. The strong force binds them, the weak force facilitates the fusion, and a torrent of energy is released. Outward pressure from this nuclear fire balances the inward crush of gravity. The star settles into a stable rhythm. It has entered the long, middle chapter of its life, the main sequence. Our sun is in this phase, shining steadily for about 4.6 billion years, and with roughly 5 billion to go. Throughout the galaxy, countless stars of various sizes share this fate, turning hydrogen into helium in their cores, pouring light and heat into space. They are like the adults of the stellar family, some smaller, cooler, and redder, burning fuel slowly and destined to live extraordinarily long, tens to hundreds of billions of years. Others much larger, hotter, and bluer, burning furiously and living fast. Just a few million years, cosmic mayflies among stars. As time flows, even stars must change. When a star exhausts the hydrogen in its core, the delicate balance tips. Fusion slows. The core begins to contract under gravity and heats up, while the outer layers, freed from the core's pressure, expand outward. For a star like the Sun, this heralds transformation into a red giant. In a deep time vision, one would see the Sun swell many times its current size, perhaps engulfing Mercury, Venus, and even Earth. Its surface cools as it expands, shifting to a luminous orange-red hue, while its core grows hotter and denser until helium can fuse into carbon. For a while, the Sun will juggle new reactions, shining not with its familiar white-yellow, but with the ruby light of old age. It may pulsate gently, shedding its outer layers in concentric waves of gas and dust. In its final breaths, it will cast off those layers entirely, creating a glowing planetary nebula, an expanding shell of gas lit by the hot, exposed core at the center. That core, no longer supported by fusion, will settle into a white dwarf, a hot, dense ember, roughly the size of Earth, but with most of the Sun's mass, slowly cooling over billions of years. The nebula will disperse into the interstellar medium, seeding space with elements the Sun forged, carbon, nitrogen, and more, gifts to the galaxy for future stars and planets. The white dwarf will fade from white to yellow to orange to red to black over trillions of years, a cinder in the darkness. Unless perhaps someday it flares again by accreting matter from a neighbor, as in a nova or supernova, if it had a companion. Such is the quiet finale for a medium star like the Sun. For stars much more massive than the Sun, the end is far more spectacular and violent. These titans, over about 8 solar masses, burn their fuel at a frantic rate, living only a few million years. They blaze hot and blue-white, and after fusing hydrogen to helium in their core, they proceed to fuse helium into carbon and oxygen, then heavier elements in layered shells, neon, magnesium, silicon, all the way to iron. Iron is a dead end. Fusing iron consumes energy instead of releasing it. So a massive star builds up an iron core like ash from a fire. Once the core is largely iron and grows to about 1.4 solar masses, it can no longer support itself against gravity. Thermal pressure and electron degeneracy pressure fail. In literally seconds, the core collapses. Protons and electrons mash together into neutrons, releasing a flood of neutrinos. The core implodes until neutron degeneracy and repulsive nuclear forces halt the collapse abruptly, and then it rebounds. This rebound, aided by neutrino pressure, launches a shockwave outward. The star's outer layers are blown off in one of nature's most cataclysmic events. A supernova explosion, briefly outshining all the billions of other stars in its galaxy. The debris, now rich in those heavy elements beyond iron, which are forged in the incredible temperatures of the explosion, is hurled into interstellar space. This supernova remnant will eventually mix with other gas and perhaps condense into new stars and planets. Meanwhile, the collapsed core remains. If the star's initial mass was moderately high, say 8 to 20 solar masses, the core becomes a neutron star, an object of mind-boggling density, about the size of a city, but with more mass than the Sun, composed mostly of neutrons. It spins rapidly. A newborn neutron star might rotate dozens of times per second, and has a powerful magnetic field, often becoming a pulsar that beams radiation like a lighthouse. If the star was extremely massive, the core collapse overwhelms even neutron degeneracy. No known force can withstand the gravity, and it continues collapsing into a black hole, a region of space-time from which nothing can escape. In either case, something remarkable happens. A once brilliant star ends in a tiny, dark remnant. If a neutron star or black hole is in a binary system, it might later accrete matter and produce X-ray emissions or further explosions, novae, X-ray bursts, etc. This cycle of stellar birth, life, and death is the heartbeat of cosmic evolution. Stars are not eternal. They are born, they mature, they grow old, and they die, often in a way that seeds the next generation. When the first generation of massive stars in the early universe died as supernovae, they produced and scattered the first heavy elements. Those enriched the gas from which new stars formed, including ones smaller, like the Sun, that could host planets with complex chemistry. Indeed, our solar system formed about 4.6 billion years ago from a cloud seeded by earlier stars' deaths, evidenced by radioactive isotopes in meteorites that are products of supernova explosions. Thus, we live in a universe where death begets new life. Supernovae create the raw material for planets and life. Even the gentle expulsion of a red giant's envelope, forming a planetary nebula, returns material to space that can be recycled. Carl Sagan's famous line, "We are made of star stuff," speaks literally true. The carbon in our proteins, the calcium in our bones, the iron in our blood, were all forged in stellar furnaces and spread by stellar deaths. Deep time connects to our very being. The evolution of galaxies. Stars live within galaxies, and galaxies themselves change over cosmic time. Galaxies can be thought of as ecosystems of stars, gas, dust, dark matter, and star clusters, all interacting. Over billions of years, galaxies grow and transform, often through mergers with other galaxies. The early universe likely had many smaller protogalaxies that gradually coalesced into the large galaxies we see today. The Milky Way, for example, has consumed several smaller galaxies in its history, and continues to do so. We see streams of stars in our halo that are remnants of devoured dwarf galaxies. Spiral galaxies like ours likely formed when smaller gas-rich pieces merged, and the combined rotation settled into a disk. Galaxies evolve from one form to another. Two spiral galaxies merging may form an elliptical galaxy, losing their delicate spiral structure in a gravitationally violent embrace and triggering massive bursts of star formation. as gas clouds collide and coalesce. Over time, ellipticals, which have little cold gas left after such bursts, become dominated by older, redder stars and have less ongoing star formation. Spirals, if left relatively unperturbed, can keep forming stars as they draw gas inward or accrete from their surroundings, but they too can run low on fuel. Our Milky Way is fated, in about 4 to 5 billion years, to merge with the Andromeda Galaxy, which is currently about 2.5 million light-years away and closing in at 110 km. Despite the enormous number of stars in each galaxy, hundreds of billions, individual stellar collisions are very unlikely due to vast interstellar spaces. However, the gravitational interaction will distort both galaxies dramatically. Over a few billion years, the two will likely settle into a single larger elliptical galaxy, sometimes dubbed Milkomeda. Simulations show their beautiful spiral arms will be thrown into chaotic streams. A burst of star formation may occur as gas clouds slam together. Ultimately, a more spheroidal distribution of stars will result. For any creatures alive then, perhaps far descendants of humanity or other intelligences, the night sky will transform. At first, Andromeda grows larger, then the sky fills with a blaze of new star formation and tidal tails of stars, and eventually it settles to a hazy glow of an elliptical galaxy filling the sky. The sun, by then a red giant or white dwarf, will find itself in a vastly altered cosmic neighborhood. Galaxies also evolve internally. Young galaxies, in the early universe, were often clumpy and irregular, forming stars at high rates. The peak of star formation in the cosmos was around 3 to 4 billion years after the Big Bang. Since then, star formation has generally declined as the big galaxies used up much of their readily available gas. Today, many large galaxies, especially ellipticals, are red and dead, forming few new stars, populated mainly by the aging population born in earlier epochs. Spirals like the Milky Way still form stars, but at a moderate pace. The Milky Way turns about 1 solar mass of gas into new stars per year. Small dwarf galaxies, especially if isolated, may still be forming stars slowly or have spurts of activity when tidal interactions occur. Galaxies can also lose gas. In clusters, where dozens to thousands of galaxies reside, a small galaxy, speeding through the hot intracluster medium, can have its gas stripped, like a breeze blowing leaves off a moving car, a process called ram pressure stripping. This leaves it without fuel for new stars, turning a blue spiral into a reddish gas-poor one. Or a galaxy might have its gas consumed by rapid starbursts or sucked into a central black hole's accretion disk, active galactic nucleus, again quenching star formation. We observe many cluster galaxies that have this quenched appearance. Speaking of black holes, nearly every large galaxy has a supermassive black hole at its center, with masses from millions to billions of suns. In youth, when gas was abundant, these black holes likely powered quasars and active nuclei, sometimes expelling jets and winds that influence their host galaxies. The interplay between central black holes and galaxy evolution is an area of active research. These black holes might help regulate star formation by heating or expelling gas, a kind of feedback. Thus, galaxies change both from external events, collisions, interactions, and internal dynamics, using up or losing gas, the effects of supernova and black hole feedback. Over deep time, the population of galaxies shifts. Fewer spirals exist now than in the past. Some have merged into ellipticals, and more ellipticals and lenticulars, disk galaxies without much gas or spiral structure, populate clusters. In the far future, as mentioned, accelerating expansion will isolate groups of galaxies. It's thought that in about 100 billion years, if dark energy remains constant, distant galaxies beyond our local group will have moved out of view, leaving future observers in our locale with only the merged Milkomeda galaxy and its satellites visible, effectively a cosmic island, with little evidence of the wider universe's existence. They would see an apparent static cosmos of one galaxy, unaware of the greater cosmic web that we now behold. Black holes and the long future. Among the remnants of deep time, black holes stand as perhaps the most enigmatic. A star leaves behind a neutron star or black hole. Galaxies have supermassive black holes at their cores. Over extremely long times, black holes may become the dominant living things as stars burn out. A typical stellar black hole, tens of solar masses, will persist far, far longer than the current age of the universe. But even black holes aren't forever. Stephen Hawking showed that they slowly evaporate by emitting Hawking radiation due to quantum effects near the event horizon. A black hole, the mass of the Sun, would take 1067 years to evaporate, an almost inconceivable span. Supermassive black holes take even longer, 100 plus years. But on the scale of deep time beyond star-filled eras, after all normal matter decays or is ejected, eventually black holes too will leak away their mass and disappear in a final burst of radiation. So imagine the stages of deep time. Now, the stelliferous era, full of stars shining. In about 100 trillion years, the last stars, likely low-mass red dwarfs and white dwarfs cooling into black dwarfs, will fade, the end of the era of starlight. What follows is sometimes called the degenerate era, the universe populated by degenerate remnants, white dwarfs, neutron stars, black holes, and cold brown dwarfs and planets. Collisions among these remnants could occasionally spark new activity. Two brown dwarfs merging might form a brief red star, or two white dwarfs colliding might ignite a supernova. But overall, it's a slow, dim time. Over quadrillions of years, gravitational encounters will gradually unbind most remaining stellar remnants from galaxies. Stars get flung out into the intergalactic void, one by one. Planets will fall into white dwarfs or be ejected. Eventually, even our Milky Way remnant, whatever it becomes after merging with Andromeda, will lose most of its constituents, and the galaxy as a gravitationally bound system will dissolve. Then comes the black hole era. After 1040 or 1050 years, depending on mass distributions, virtually everything left gravitating in lumps are black holes, from massive ones to possibly an army of micro-black holes, if any were created, though unlikely naturally. They slowly evaporate. The universe is dark except perhaps for occasional flashes when black holes finish evaporating, or rare collisions between remnants. After an absurdly long time, all black holes evaporate too. We reach the final stage. Some call the dark era. Only subatomic particles remain, mostly photons, neutrinos, electrons, and positrons, spread so thin across an ever-expanding cosmos that on average years of travel would be required to hit another particle. The temperature everywhere will be effectively absolute zero, apart from quantum fluctuations. The cosmos will have reached maximum entropy, no available free energy to do anything, essentially a quiet heat death. This long view, from bright Big Bang to faint heat death, is mind-bending. It makes our era of galaxies and stars and life seem like a fleeting springtime in the cosmos. And indeed, it is. Yet knowing this timeline can inspire an even greater appreciation for the now. We live in a special time when the universe is full of light and complexity. The deep future, though bleak in prospect, is fortunately trillions of times farther away than the current universe's age, so for all practical purposes, the cosmos will remain lively far, far longer than it has existed so far. Deep time narratives invite us to face both the resilience and impermanence of the cosmos. Stars die, but their remains fertilize new stars. Galaxies collide destructively, but forge new stars in the process. Even black holes might eventually die, but perhaps releasing whatever information they held. Through an emotional lens, these are stories of cosmic reincarnation and renewal, followed eventually by an end of things. An arc with a beginning and end, just as mythologies had, but on incomprehensible scales. To an immortal being watching eons pass, the universe would appear as a vast garden. Stars bloom like cosmic flowers, some short-lived and brilliant, others steady and enduring, then wither, their substance becoming the seeds of new blooms. Galaxies grow by gathering these blooms, sometimes pruning each other in collisions, and eventually many go to seed themselves as diffuse clouds. The garden analogy falters by the end of time, when darkness covers all. But by then, the garden had given all it could. For us, understanding deep time is at once enlightening and sobering. It contextualizes our brief lives in something far larger. It reminds us that change is constant. No arrangement of matter lasts forever. Yet it also shows how creative the universe has been in the time allotted, going from near uniform gas to conscious beings pondering it all. Now, with a grasp of deep time's canvas, we can zoom back to our human scale and ask, how do we, conscious flickers in this vast unfolding, fit in? The next chapter turns to the emergence of something arguably as remarkable as any galaxy, consciousness, which allows the cosmos to reflect on itself. Scale. As we zoom from the cosmic to the minute, we encounter a remarkable truth. Patterns repeat and echoes sound across vastly different scales. The universe is structured hierarchically, from subatomic particles up through atoms, molecules, planets, stars, galaxies, and the cosmic web. And while each layer has its unique phenomena, sometimes the small and large reflect each other in surprising ways. Imagine scaling down from human size. Shrink 1 billion times. You stand at the edge of an atom, electrons whizzing in a cloud around a tiny nucleus. The nucleus, if you peeked in, is itself a swarm of protons and neutrons, bound tightly by the strong force. Dive further. Inside a proton, you'll find quarks darting amid a sea of gluons. This is a world measured in femtometers, 10 to 15 me, and less, a far cry from everyday scales. Now zoom out, past human scale to planetary and beyond. The Earth orbits the Sun at 150 million kelm. The Sun orbits the center of the Milky Way, 27,000 light-years away, along with hundreds of billions of other stars. Our galaxy, 100,000 light-years across, is one of perhaps 100 billion in the observable universe. The largest coherent structures we see, walls of galaxies and voids, span a few billion light-years. That's a factor of about 10,040 from the Planck length, 10 to 35 maths, believed to be a fundamental scale of quantum gravity, to the observable universe's diameter, 10 to 27 maths. Yet through this immense range, the same fundamental principles operate. Gravity holds planets in orbit much as it holds galaxies in clusters, just with different relative influences of other forces. Electromagnetism binds an electron to an atomic nucleus and similarly governs the structure of a star via plasma interactions. The forces of nature are scale-blind. They work everywhere, with only their effects modulated by environment. The small and the large often mirror each other. Consider a hydrogen atom, a tiny nucleus with electrons in orbit, historically likened to a miniature solar system. That analogy isn't perfectly accurate. Quantum mechanics shows electrons are in fuzzy probability clouds, not neat orbits. But the structural motif of a central mass with orbiting bodies recurs. Electrons around nuclei, moons around planets, planets around stars, stars around galaxy centers. The binding forces differ, electromagnetic versus gravitational, but the resulting patterns have a visual resonance. A spiral galaxy with its arms may evoke the swirl of water down a drain, or the spiral of a hurricane, not because they are caused by the same reasons, gravity versus pressure and Coriolis forces, but because rotating systems often settle into spirals to conserve angular momentum and form density waves. One fascinating comparison: the cosmic web of galaxies and the network of neurons in a brain have been noted to share similar filamentary structures. One is billions of light years across, the other confined to a skull, but both are vast networks shaped by growth rules. A 2020 study even quantified similarities in the distribution of matter in the cosmic web and neural networks. While obviously the physics differ, the abstract analysis of connectivity showed parallels in complexity. It's a reminder that complexity can emerge from simple rules at multiple scales, sometimes yielding convergent structures. Our sense of scale is very limited to the human range. We measure in meters and seconds suited to our everyday life. But the universe extends far above and below those. A cosmic perspective forces us to accommodate scales where our intuition fails. It's mind-bending that an atomic nucleus, with its protons and neutrons, is as small relative to us as the sun is large relative to us. We sit roughly in the middle of logarithmic scales, about 10 2 meters in size. On a log plot from the Planck length to the universe, humans are not far from center. In a way, we have 1 foot in the micro-world. We can examine things as small as molecules and atoms with effort, and 1 foot in the cosmic. We can see galaxies and clusters with our telescopes. Perhaps this accident of scale is what allowed us as a species to comprehend things far beyond our direct sensory realm. We evolved in a world where both small and large phenomena affected us, from grains of sand to the cycling sun and moon, giving us curiosity in both directions. And indeed, modern science is a triumph of exploring both the very small and very large. By going down to subatomic scales, we've uncovered the fundamental particles and forces, enabling technologies like electronics and nuclear energy. By going up to cosmic scales, we've discovered the Big Bang, cosmic expansion, and the age of the universe. The fact that the human mind, a small-scale object itself, can grasp scales 10-20 times smaller and 10-20 times larger than itself is astonishing. It's a testament to mathematics and imagination that we can conceptualize things so far outside direct experience. Another connection across scales is that the very large was seeded by the very small. Quantum fluctuations, random tiny variations at the subatomic level, during the epoch of inflation in the extremely early universe, were blown up to macroscopic size, laying down the pattern for the cosmic web. Thus, the distribution of clusters and voids we see today is in part a fossil record of quantum events in the first 10 to 30 seconds of the universe. The microscopic shaped the telescopic. This is almost poetic. The initial graininess on the quantum level became the literal grains, galaxies, in the cosmic structure. Conversely, understanding large-scale processes often helps reveal small-scale physics. For example, observing the nuclear reactions in the Sun via neutrinos and helioseismology confirmed our knowledge of particle physics, like the properties of neutrinos. The solar neutrino problem and its resolution in neutrino oscillations showed neutrinos have mass, a small-scale property discovered by looking at a star. Cosmology data, like the microwave background and element abundances, provide evidence for particle physics phenomena, like the existence of relativistic species, neutrinos, in the early universe. In summary, the cosmos is truly fractal-like in its wonders. Patterns and principles iterate, and insight at one scale often informs another. We find ourselves at an intermediate scale, but equipped with tools and reason to traverse the extremes. By doing so, we realize that we are not isolated at our scale. We are made of subatomic particles, and we orbit a star in a galaxy. We contain multitudes of atoms, and we are part of something larger, the universe. Embracing this multi-scale reality adds to our awe. The next time you hold a salt crystal, consider that within its tiny cubic structure lies a microcosm of electromagnetic forces and quantum rules, not entirely unlike the gravitational lattice of galactic clusters spanning millions of light years. The salt's sodium and chlorine atoms form a repeating pattern, just as galaxies form a weave in space. Patterns at vastly different scales can still rhyme. Now, stepping back from scale and structure, we venture into what might be the strangest aspects of the cosmos. Those that challenge our understanding not just of size or shape, but of reality itself. Black holes that warp space-time, mysterious dark matter and dark energy that we detect only indirectly, hypothetical wormholes that might tunnel through space-time, and other unknowns that remind us how much more there is to learn. It's time to explore the strange cosmos, the mysterious components and possibilities that push the boundaries of known physics. The strange cosmos. For all that we have learned, the cosmos still guards many secrets. In fact, the more we've discovered, the more we've realized how much lies in darkness, hidden from direct perception. The night sky we see, with its stars and galaxies, is only a thin slice of reality. The rest is filled with mysteries, unseen matter and energy, space-time oddities, cosmic phenomena that challenge our intuition. Among these enigmas are black holes, dark matter, dark energy, and the hypothetical wormholes and parallel universes that tantalize physicists and philosophers alike. These are the strange elements of the cosmos that make it not just vast, but deeply mysterious. Black holes, the abyss of space-time. Perhaps nothing in the universe is as foreboding and fascinating as a black hole. Imagine a star 10 times the sun's mass reaching the end of its life. Its core fuel spent, it collapses under its own weight. If nothing stops the collapse, and for a massive core nothing will, it shrinks past the formation of a neutron star, past any known stable form, to a point, a singularity, of seemingly infinite density. All that mass is now concentrated in zero volume, and gravity around it becomes so intense that within a certain radius, the event horizon, not even light can escape. A black hole is born, an object with a one-way surface. Cross the event horizon, and you cannot return or send a message out. To the outside world, you effectively vanish. Black holes take our understanding of physics to the edge. According to Einstein's general relativity, mass curves spacetime. A black hole is an extreme curvature where spacetime essentially pinches off. Time and space swap roles in a sense. Moving forward in time inevitably carries you inward toward the singularity if you're inside the horizon. Quantum physics adds further mystery. At the event horizon, quantum effects can create particle pairs, leading to Hawking radiation, meaning black holes aren't completely black. They glow faintly and lose mass over time. We have strong evidence black holes exist. Stellar black holes announce themselves by gravitational effects on companions and by emitting X-rays when consuming gas. We have imaged the shadow of a 6 billion solar mass black hole in galaxy M87 via the Event Horizon Telescope, seeing a ring of light from hot gas and a dark center where the hole's gravity prevents light from coming directly to us. We see stars at the center of our Milky Way whipping around an invisible 4 million solar mass object at speeds of thousands of km/h. Definitely a supermassive black hole. So black holes are not just theoretical. They are out there. Commonplace, in fact. Every large galaxy likely has one, and many stellar remnants become black holes. They distort reality around them. Clocks near a black hole run slower relative to far away. To a distant observer, a clock falling toward a black hole appears to tick ever slower and essentially freeze at the horizon, though the clock itself experiences falling through normally. If you fell in, past tidal forces ripping you apart, if it's a small hole, you might have some time to observe near the singularity, but ultimately you'd be crushed, and what's inside the horizon is cut off from our universe, so it's like you've left our reality. Black holes are strange because they present a breakdown of our laws. A singularity is a sign that general relativity gives infinite results, meaning the theory breaks down there. It's expected that quantum gravity, a future theory uniting GR and quantum mechanics, will resolve what happens at the core. Do singularities exist, or are they replaced by something like a quantum fuzz or bounce? Also, do black holes destroy information? Quantum theory says information, the specifics of matter that fell in, should be preserved in some form. This has led to the famous black hole information paradox. Many physicists now think information does escape in subtle form via Hawking radiation or is stored in correlations, meaning black holes might not erase information entirely, no cosmic delete button, just very scrambled output. Even more exotic is speculation that a black hole could connect to another region of space-time, a wormhole. In principle, the mathematics of GR allow an Einstein-Rosen bridge connecting two black holes, or a black hole and a hypothetical white hole, essentially a tunnel. But such wormholes, if they exist, would be unstable. They'd pinch off unless held open by negative energy, exotic matter. We have no evidence wormholes exist naturally. They might be purely theoretical or require technology far beyond us to stabilize. Still, they captivate the imagination as cosmic shortcuts or even time machines, since wormholes potentially could allow travel back in time, raising paradoxes. Dark matter, the hidden mass. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in the outer parts of spiral galaxies and found something odd. They were moving as fast as stars closer in. According to Newtonian gravity, stars far from the galactic center should orbit more slowly if most mass is concentrated in the center, like planets in the solar system. Instead, galaxy rotation curves flatten out, indicating there's much more gravity, and hence mass, in the outskirts than can be accounted for by visible stars and gas. Similarly, clusters of galaxies have galaxies moving too quickly to be held together by the visible mass alone, and gravitational lensing, the way clusters bend background light, indicates more mass than seen. The conclusion: most of the matter is unseen, dubbed dark matter. Dark matter seems to interact gravitationally, but not, or extremely weakly, via electromagnetic or nuclear forces. It doesn't emit, absorb, or scatter light, hence dark. It's not made of atoms. It's something else, likely some kind of particle left over from the Big Bang that we have yet to detect in the lab. It outweighs normal matter roughly 5.1 in the universe. It's the scaffolding on which galaxies formed, as discussed in the cosmic web. Without dark matter, our models struggle to form galaxies as observed, and structures might not hold together. Despite decades of trying, we haven't directly observed dark matter particles on Earth. Various underground detectors have looked for them hitting nuclei, without confirmed success yet, or created them in colliders. We infer their existence from their gravitational effects. The leading hypothesis is that dark matter is some kind of WIMP, weakly interacting massive particle, left from the early universe, or possibly an axion, a very light particle, or something more exotic like a dark sector with its own forces. But so far, it's a shadowy presence, clearly there, yet elusive. Some have proposed alternative gravity theories, like MOND, modified Newtonian dynamics, or various relativistic extensions, to eliminate the need for dark matter by changing how gravity works at galaxy scales. While these can fit some galaxy rotation curves, they struggle with cluster lensing and the cosmic microwave background data that strongly support the dark matter paradigm. The simplest consistent explanation remains a dominant component of unseen matter. So, to an extent, we live in a shadow universe. Only about 1/6 of matter is the familiar atoms that make up stars, planets, and us. The rest, plus an even larger fraction in dark energy, which we'll get to, is hidden. It's humbling. All the glowing galaxies are like a froth on a vast dark ocean of matter. Without that ocean, though, the froth wouldn't exist. Dark matter's gravity was essential to gather normal matter into galaxies. Dark energy, the runaway expansion. In 1998, two teams measuring distances to fast supernovae made a shocking discovery. Distant Type Ia supernovae were dimmer than expected, indicating they were farther than they should be if the universe's expansion was slowing down. Put simply, the expansion of the universe has been speeding up in the last few billion years. This was the opposite of what most expected. Gravity from matter should slow expansion. The cause was dubbed dark energy, a mysterious form of energy that fills space and drives accelerated expansion. It's often associated with the cosmological constant, L, concept that Einstein once introduced and famously discarded as a blunder when he thought the universe was static, now revived as a physical reality. Dark energy is even more enigmatic than dark matter. It constitutes about 68% of the universe's total energy content. We don't know what it is. If it's a true cosmological constant, it's an inherent property of space. Every cubic meter of vacuum has some fixed tiny energy, around 6 by 10 hours to 10 joules, that doesn't dilute as space expands. So as space grows, more vacuum means more total energy, causing expansion to accelerate. Alternatively, dark energy might be a field that can change over time, sometimes called quintessence, or something even more exotic, like an effect of other dimensions or a flaw in GR on huge scales. So far, all observations, supernova, cosmic microwave background, large-scale structure, are consistent with dark energy being a constant property of space, with an equation of state parameter, WL1, in cosmological terms. If it remains so, the fate is an ever-accelerating expansion. Galaxies outside our local group will recede faster and faster until they become unreachable and eventually invisible. Dark energy seems to have become dominant a few billion years ago. Prior to that, matter's gravity was slowing expansion. But as the universe expanded, matter diluted, density dropping as volume increases, whereas dark energy, as a constant density, did not. Eventually, matter's influence waned and dark energy took over, causing expansion to accelerate. Why dark energy has the value it does is a huge puzzle. Quantum zero-point energy calculations naively predict a cosmological constant, 10^120 times larger, which would have blown the universe apart instantly after the Big Bang. A gross discrepancy, one of the biggest in physics. Something, perhaps a cancellation mechanism we don't understand, leaves a small residual that is our dark energy. That's a major unsolved problem. If dark energy is constant, the universe will approach a de Sitter state, exponential expansion forever. If it's not constant, who knows? Some theorize dark energy could decay or even reverse, leading to a big crunch or oscillation, but no evidence of such behavior yet. So we live in a universe where about 95% of its content is in two invisible forms, dark matter and dark energy. It's as if we have a book where only some letters are visible and the rest are in invisible ink. We're trying to read the story from the few visible letters and a lot of blank spaces. Yet the visible letters, stars, galaxies, etc., give us enough clues through their dynamics and arrangements to infer what's missing. Wormholes and other wild ideas. The notion of wormholes, shortcuts through space-time, has long captured imagination. Solutions of Einstein's equations, like the Schwarzschild wormhole, which is the non-traversable mathematical connection in a black hole solution, or the traversable Morris-Thorne wormholes that require exotic matter with negative energy, indicate such tunnels are not forbidden by general relativity outright. But whether nature actually makes any is unknown. If cosmic strings, defects in space-time from early universe phase transitions, or certain quantum fluctuations occurred, some think it might be possible a few wormholes were spawned, but they'd likely collapse quickly or be extremely tiny. No evidence exists for any. If one could stabilize a wormhole, it could allow faster than light travel, effectively by taking a shortcut. or even time travel, depending how the wormhole mouths move relative to each other. But physics as we know it strongly suggests causality violations are not allowed. Time travel leads to paradoxes, though closed, time-like curves can exist in theory. Most physicists suspect some deeper principle prevents actual time machines. Another wild idea: maybe our whole universe is a patch inside a larger multiverse, where other universes have different physical constants or particles. Inflation theory suggests space might be much larger than our observable part, possibly with other bubble universes disconnected from ours. If so, maybe constants like gravity's strength or protons' mass could vary in those bubbles. That could partially explain why our constants are tuned for life, anthropic selection from many universes. But this remains speculative and arguably untestable. We can't observe other universes if they're truly disjoint. Some signatures like colliding bubble universes might imprint something in our cosmic background, but none clearly seen. It might be that what we call constants of nature are not fixed in space-time either. There are studies testing if, say, the fine structure constant, electromagnetic strength, or electron-proton mass ratio has changed over cosmic time by analyzing ancient light. So far, results are mostly consistent with no change, or changes so slight they remain debated. If any drift exists, it's very tiny, meaning the laws today were essentially the laws 10 billion years ago. All these strange aspects, wormholes, multiverses, varying constants, stretch the boundaries of the known. They are at the edge of science and veer into philosophy at times because they're hard to verify or falsify. Still, exploring them is valuable. It expands our conception of what might be possible and forces us to confront the assumptions in our accepted theories. Embracing mystery. Confronting the strange cosmos instills humility. We see that our knowledge, while vast compared to the ancients, may still be scratching the surface. We uncovered dark matter and energy by their gravitational footprints, but we don't yet know their identities. We theorized black holes from relativity, then found they are real astrophysical objects, yet at their core lies the need for a new theory, quantum gravity, to understand singularities. We use quantum mechanics and relativity daily in our devices and GPS, yet their reconciliation into one framework eludes us, hinting at deeper layers of reality. The strange elements of the cosmos are clues that the story isn't finished. There are chapters of physics yet to be written, perhaps by future generations. And yet, rather than these unknowns making the universe seem alien, they can also inspire a sense of being part of a grand quest. We alive today are among the first generation to know that dark matter and dark energy exist. Perhaps one day a child today will solve the riddle of dark matter in a lab experiment or theory. We stand on a threshold where the cosmos is telling us there's more here than meets the eye. In grappling with the strange, we also find a reassuring continuity. Every time our view expanded or was challenged by Copernicus, by Hubble, by dark energy's discovery, we eventually integrated it and found our understanding actually deepened and often benefited humanity. Imagine modern tech without quantum mechanics or relativity, which were once strange new ideas. So there is faith, born of experience, that confronting the unknown is worthwhile, and reality, however strange, is ultimately comprehensible, as Einstein mused. Now, having explored the structure and mysteries of the external cosmos, we turn inward to perhaps the most remarkable outcome of cosmic evolution, ourselves, conscious beings capable of reflecting on the cosmos. We examine how the universe, through life and mind, has awakened to itself, and what that means for meaning and perspective. Consciousness. At some point in cosmic history, the cosmos became aware of itself, on at least one planet and perhaps countless others, a collection of atoms organized in such a way that it could ponder the very stars that made its constituents. This phenomenon, consciousness, is the most complex and mysterious form of order we know. Through us, and beings like us, the universe has eyes to see and minds to contemplate its own vastness. Carl Sagan put it poetically, "We are a way for the universe to know itself." The journey to consciousness was gradual and took billions of years on Earth. Simple life emerged at least 3.5 billion years ago in Earth's oceans, likely as self-replicating molecules that became enclosed in membranes, primitive cells. These life forms could sense and respond. Even a bacterium will move toward nutrients or away from harm. That's a rudimentary form of awareness, not thought, but biological feedback. Multicellular life allowed differentiation, specialized cells for sensing, like light-sensitive patches that became eyes, and for processing, simple neural nets. By the Cambrian explosion, 540 million years ago, complex animals with eyes and nervous systems filled the seas, presumably experiencing basic perceptions. Fast forward, vertebrates developed more complex brains. Some lineages crawled onto land. In mammals, the brain's cortex expanded, enabling memory, learning, and emotion. At some indeterminate point, early humans or their ancestors achieved self-awareness, an ability not just to feel or learn, but to know that they know, to reflect on one's own existence. Consciousness is hard to define but intimately known to each of us. It's the subjective experience of internal and external reality. It's the I am behind your eyes, the experiencer of your life. Scientifically, we map its correlates, brain patterns, neural oscillations, integrated information, but we don't truly understand how the grey matter of the brain produces the bright light of consciousness. This is the hard problem of consciousness. Yet, it undeniably does, at least in humans, and likely other animals to varying degrees. From a cosmic perspective, consciousness is profound because it seems qualitatively different from unconscious matter. The ingredients that make a human, oxygen, carbon, hydrogen, nitrogen, calcium, etc., are common in the cosmos, in air and rock and sea, but arrange them in the exquisite complexity of a living cell, then an organ, then a brain, and something novel emerges, mind. It raises a question. Is consciousness a fundamental aspect of the universe? Some philosophers and physicists have toyed with panpsychism, that consciousness might be a property of matter under certain conditions. Or is it an emergent phenomenon requiring a certain level of complexity? Either way, the potential for mind was built into the cosmos from the start, in the sense that the laws of physics allowed matter to self-organize into conscious forms. When the universe was a hot plasma, it had no structures at all, let alone life. But it cooled, matter clumped, stars forged heavier elements, planets formed with complex chemistry, life sparked and evolved, and eventually, those ancient atomic nuclei, born in the hearts of stars, became part of a thinking being that can look back and say, "Wow, I come from the stars." The cosmos became aware of its origins through our minds. This confers a sense of purpose, in a way. Not an externally assigned purpose, but a role we naturally play. We are the cosmos, in one of its latest evolutionary phases, marveling at itself. When we discover things about the universe, it is literally the universe discovering itself. Our joy of comprehension is the universe taking joy in self-comprehension. Consciousness also heightens the emotional stakes of cosmic knowledge. Without conscious beings, the grand universe simply is, with no one to admire a nebula or fear a black hole. With consciousness, beauty and terror enter the scene. Think of the first humans fearful of eclipses or awestruck by the Milky Way. The cosmos evokes feelings now because we feel. Through us, the universe has emotion and meaning, at least locally. A nebula is not objectively beautiful, but we find it so, giving aesthetic dimension to existence that wouldn't exist without minds. Many scientists and philosophers suspect life and possibly consciousness might not be unique to Earth. If biology is a natural outcome on wet, rocky worlds under the right conditions, and evolution often fosters intelligence given enough time, then perhaps the cosmos teems with other conscious beings. They may not be human-like, but they could wonder and seek as we do. Perhaps the universe has many centers of consciousness scattered among the galaxies, a kind of cosmic self-awareness shining in many places. Or perhaps not. Maybe intelligent life is extremely rare. We don't know yet. Either answer, teeming life or cosmic solitude, is profound. If we are among many, what a grand community awaits discovery, though distances are forbidding. If we are alone, or nearly so, what a precious flame of awareness we bear, and what responsibility to not squander it. Consciousness gives the universe a way to know time in a meaningful way too. Without minds, time just passes. With minds, the passage of time is felt. We have memory of the past and anticipation of the future. We seek patterns and thus uncover cosmic history, like figuring out the Big Bang, and cosmic future, heat death or other fates. In a sense, by becoming aware of deep time, we have extended the reach of consciousness to the entire lifespan of the universe. Mentally, we travel to the beginning and to hypothetical ends. The universe through us can contemplate its entire existence, almost like how we as individuals reflect on our own lives. There is also a contemplative aspect. Many find that recognizing we are the universe coming to consciousness can be spiritually meaningful. It collapses the divide between me and world. In a cosmic sense, the distinction is indeed arbitrary. We're made of the world and return to it. As conscious beings, we can feel empathy not just to other living things, but to the stars and the atoms, feeling a unity with all. Some spiritual traditions echo this scientific truth. We are one with the universe. As we move forward, conscious of our conscious role, we might ask, what next for the cosmos and consciousness? Will our awareness fade when humanity, or life, ends, or will it spread? Some dream of humanity expanding to other planets, carrying consciousness further through the cosmos. In doing so, giving the universe more places where it can reflect on itself. Others consider that artificial intelligence might carry consciousness, or at least intelligence forward, even if biological life fails. It's a speculative territory, but the point remains. Through our minds, the universe has reached a level of self-reflection, and what we do with that is, to some extent, up to us. Having considered mind and meaning, let's pull back one last time to the broadest perspective. Is our universe the only one? Or could there be a multitude, a multiverse? And is the structure of reality fundamentally made of something like information or math, rather than tangible matter? These are deep questions at the intersection of physics and philosophy. We touch on them briefly, as they color the ultimate context in which our cosmos might reside. The multiverse. Is our universe unique, or one of many? For ages, universe meant all there is. But modern physics has opened the door to the idea that our universe might be a bubble in a froth of countless universes. A multiverse. This concept arises from several lines of thought. One is cosmic inflation, the idea that a fraction of a second after the Big Bang, space expanded exponentially fast. Inflation theory, in many versions, suggests that inflation didn't end everywhere at once. It ended in patches, like our universe, while other regions kept inflating, budding off other bubble universes. If eternal inflation is correct, our universe may be one domain among an indefinitely large, possibly infinite number of domains, each a universe in its own right, with potentially different properties. Another motivator is fine-tuning. We observe that certain fundamental constants, like the strength of electromagnetism or the dark energy density, have values in a narrow range that allows complexity, galaxies, stars, life, to exist. It's puzzling why they have just those life-permitting values. One possible explanation is the anthropic principle combined with a multiverse. If indeed many universes exist with varying constants, we naturally find ourselves in one of the minority that by chance has the right conditions for observers, because only such universes get observers. It's like we shouldn't be surprised to live on Earth rather than on Jupiter. Only Earth had the proper conditions for our kind of life. Similarly, maybe only a small fraction of universes have viable physics for any form of complexity, and of course, we must be in one of those. If the multiverse idea is true, reality is much bigger than we can see. Our observable cosmos, the 93 billion light-year bubble of space we can currently observe, would be just a tiny patch in an inconceivably vast inflating space that contains other bubbles beyond our horizon. We cannot directly communicate with or travel to those other universes. Space between us and them is still inflating, or they're causally disconnected. But their existence would answer some otherwise intractable why questions by essentially saying everything happens somewhere. We see what we see because those conditions are necessary for us to exist. In some multiverse scenarios, the basic laws might differ. Perhaps one universe has a slightly stronger, strong force, which might mean no hydrogen, all protons fuse into heavier elements quickly, or a slightly weaker electromagnetic force. Maybe stars can't form because fusion won't ignite. There might even be universes with different numbers of spatial dimensions or different particle types. The possibilities are vast in principle. We don't know if physical constants can vary like that. But string theory, for instance, predicts a landscape of possible vacuum states with different properties, and eternal inflation could populate different regions with different vacuum states, hence different constants and particle physics. It's almost a philosophical question. Are these other universes real if we can never observe them? Some say if a theory that predicts them also robustly predicts things we can observe, and the theory is validated, then we must accept whatever else it entails, like unseen universes. Others argue that non-disprovable entities are not within science's remit. Currently, the multiverse is a hypothesis, intriguing, sometimes seemingly implied by theories but not confirmed. Parallel to the cosmological multiverse is the idea from quantum mechanics of the many worlds interpretation, that every quantum event that has multiple outcomes, electron goes left or right, spawns branches of reality for each outcome. In that view, all possible histories consistent with quantum probabilities play out in a vast branching of universes. This is a different beast than the inflationary multiverse. These universes occupy the same space but in different quantum branches, rather than separate bubbles of space. But interestingly, both ideas paint a picture of numerous alternate realities. If both were true, it could be an unimaginably enormous collection of universes, bubble universes, each with internal branching quantum worlds. These ideas challenge our notion of uniqueness. It might make one feel small. Not only are we one tiny planet in a vast universe, but our entire universe might be one grain of sand on an endless cosmic shore. But one can also find it empowering. If indeed our universe is rare enough to permit life, how lucky we are to experience it. If universes are countless, then the creative potential of reality is truly without limit. Whatever can happen will happen somewhere, perhaps many times over. One might ask, how does multiverse thinking affect daily life or meaning? Perhaps not much. True or not, it doesn't change the tangible universe we interact with. But it adds another layer to the grand perspective, maybe even our entire cosmic cosmos, a journey through space and time.